Chapter 3, Origin of the Species by Means of Natural Selection, 6th edition. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Chapter 3, The Struggle for Existence. Its bearing on natural selection, the term used in a wide sense, geometrical ratio of increase, rapid increase of naturalized animals and plants, nature of the checks to increase, competition universal, effects of climate, protection from the number of individuals, complex relations of all animals and plants throughout nature, struggle for life most severe between individuals and varieties of the same species, often severe between species of the same genus, the relation of organism to organism, the most important of all relations. Before entering on the subject of this chapter, I must make a few preliminary remarks on how the struggle for existence bears on natural selection. It has been seen in the last chapter that among organic beings in a state of nature there is some individual variability. Indeed, I am not aware that this has ever been disputed. It is immaterial for us whether a multitude of doubtful forms be called species or subspecies or varieties, what rank, for instance, the 200 or 300 doubtful forms of British plants are entitled to hold, if the existence of any well-marked varieties be admitted. But the mere existence of individual variability and of some few well-marked varieties, though necessary as the foundation for the work, helps us but little in understanding how species arise in nature. How have all those exquisite adaptations of one part of the organization to another part, and to the conditions of life, and of one organic being to another being, been perfected? We see these beautiful co-adaptations most plainly in the woodpecker and the mistletoe, and only a little less plainly in the humblest parasite which clings to the hairs of a quadruped or feathers of a bird, in the structure of the beetle which drives through the water, in the plumed seed which is wafted by the gentlest breeze. In short, we see beautiful adaptations everywhere and in every part of the organic world. Again, it may be asked, how is it that varieties, which I have called incipient species, become ultimately converted into good and distinct species, which in most cases obviously differ from each other far more than do the varieties of the same species? How do those groups of species which constitute what are called distinct genera, and which differ from each other more than do the species of the same genus, arise? All these results, as we shall more fully see in the next chapter, follow from the struggle for life. Owing to this struggle, variations, however slight, and from whatever cause proceeding, if they may be in any degree profitable to the individuals of a species, in their infinitely complex relations to other organic beings, and to their physical conditions of life, will tend to the preservation of such individuals, and will generally be inherited by the offspring. The offspring also will thus have a better chance of surviving, for, of the many individuals of any species which are periodically born, but a small number can survive. I have called this principle, by which each slight variation, if useful, is preserved, by the term natural selection, in order to mark its relation to man's power of selection. But the expression is often used by Mr. Herbert Spencer, of the survival of the fittest, is more accurate, and is sometimes equally convenient. We have seen that man by selection can certainly produce great results, and can adapt organic beings to his own uses, through the accumulation of slight but useful variations given to him by the hand of nature. But natural selection, we shall hereafter see, is a power incessantly ready for action, and is as immeasurably superior to man's feeble efforts as the work of nature are to those of art. We will now discuss in a little more detail the struggle for existence. In my future work this subject will be treated, as it well deserves, at greater length. The elder de Candolle and Lyell have largely and philosophically shown that all organic beings are exposed to severe competition. In regard to plants, no one has treated this subject with more spirit and ability than W. Herbert, Dean of Manchester, evidently the result of his great horticultural knowledge. Nothing is easier than to admit in words the truth of the universal struggle for life, or more difficult, at least I found it so, than constantly to bear this conclusion in mind. Yet unless it be thoroughly ingrained in the mind, the whole economy of nature, with every fact on distribution, rarity, abundance, extinction, and variation, will be dimly seen or quite misunderstood. We behold the face of nature bright with gladness. We often see superabundance of food. We do not see, or we forget, that the birds which are idly singing round us mostly live on insects or seeds, and are thus constantly destroying life. Or we forget how largely these songsters, or their eggs, or their nestlings, are destroyed by birds and beasts of prey. We do not always bear in mind that though food may be now superabundant, it is not so at all seasons of each recurring year. The term struggle for existence, used in a large sense. I should premise that I use this term in a large and metaphorical sense, including independence of one being on another, and including, which is more important, not only the life of the individual, but success in leaving progeny. Two canine animals, in a time of death, may be truly said to struggle with each other, which shall get food and live. But a plant on the edge of a desert is said to struggle for life against drought, though more properly it should be said to be dependent on the moisture. A plant which annually produces 1,000 seeds, of which only one of an average comes to maturity, may be more truly said to struggle with the plants of the same kind and other kinds which are already clothing the ground. The mistletoe is dependent on the apple and a few other trees, but can only in a far-fetched sense be said to struggle with these trees, for, if too many of these parasites grow on the same tree, it languishes and dies. But several seedling mistletoes, growing close together on the same branch, may more truly be said to struggle with each other. As the mistletoe is disseminated by birds, its existence depends on them, and it may metaphorically be said to struggle with other fruit-bearing plants, in tempting the birds to devour and thus disseminate its seed. In these several senses which pass into each other, I use for convenience' sake the general term struggle for existence. Geometrical ratio of increase. A struggle for existence inevitably follows from the high rate at which all organic beings tend to increase. Every being which during its natural lifetime produces several eggs or seeds must suffer destruction during the same period of its life, and during some season or occasional year. Otherwise, on the principle of geometrical increase, its numbers would quickly become so inordinately great that no country could support the product. Hence, as more individuals are produced than can possibly survive, there must in every case be a struggle for existence, either one individual with another of the same species, or with the individuals of distinct species, or with the physical conditions of life. It is the doctrine of Malthus, applied with manifold force to the whole animal and vegetable kingdoms. For in this case there can be no artificial increase of food, and no prudential restraint from marriage. Although some species may be now increasing, more or less rapidly, in numbers, all cannot do so, for the world would not hold them. There is no exception to the rule that every organic being naturally increases at so high a rate, that, if not destroyed, the earth would soon be covered by the progeny of a single pair. Even slow-breeding man has doubled in 25 years, and at this rate, in less than 1,000 years, there would literally not be standing room for this progeny. Linnaeus has calculated that if an annual plant produced only 2 seeds, and there is no plant so unproductive as this, and their seedlings next year produced 2, and so on, then in 20 years there would be 1,000,000 plants. The elephant is reckoned the slowest breeder of all known animals, and I have taken some pains to estimate its probable minimum rate of natural increase. It will be safest to assume that it begins breeding when 30 years old, and goes on breeding till 90 years old, bringing forth 6 young in the interval, and surviving till 100 years old. If this be so, after a period from 740 to 750 years, there would be nearly 19 million elephants alive descended from the first pair. But we have better evidence on this subject than mere theoretical calculations, namely the numerous recorded cases of the astonishingly rapid increase of various animals in a state of nature, when circumstances have been favourable to them during 2 or 3 following seasons. Still more striking is the evidence from our domestic animals of many kinds which have run wild in several parts of the world. If the statements of the rate of increase of slow-breeding cattle and horses in South America, and latterly Australia, had not been well authenticated, they would have been incredible. So it is with plants. Cases could be given of introduced plants which have become common throughout whole islands in a period of less than 10 years. Several of the plants, such as the cardoon and tall thistle, which are now the commonest over the wide plains of La Plata, clothing square leagues of surface almost to the exclusion of every other plant, have been introduced from Europe. And there are plants which now range in India, as I hear from Dr. Falconer, from Cape Comorin to the Himalaya, which have been imported from America since its discovery. In such cases, and endless others could be given, no one supposes that the fertility of the animals or plants has been suddenly and temporarily increased in any sensible degree. The obvious explanation is that the conditions of life have been highly favourable, and that there has consequently been less destruction of the old and young, and that nearly all the young have been enabled to breed. Their geometrical ratio of increase, the result of which never fails to be surprising, simply explains their extraordinarily rapid increase and wide diffusion in their new homes. In a state of nature, almost every full-grown plant annually produces seed, and among animals there are very few which do not annually pair. Hence we may confidently assert that all plants and animals are tending to increase at a geometrical ratio, that all would rapidly stock every station in which they could anyhow exist, and that this geometrical tendency to increase must be checked by destruction at some period of life. Our familiarity with the larger domestic animals tends, I think, to mislead us. We see no great destruction falling on them, and we do not keep in mind that thousands are annually slaughtered for food, and that in a state of nature an equal number would have somehow to be disposed of. The only difference between organisms which annually produce eggs or seeds by the thousand and those which produce extremely few is that the slow breeders would require a few more years to people, under favourable conditions, a whole district, let it be ever so large. The condor lays a couple of eggs and the ostrich a score, and yet in the same country the condor may be the most numerous of the two. The fulmar petrel lays but 1 egg, yet is believed to be the most numerous bird in the world. One fly deposits hundreds of eggs, and another, like the hippobosca, a single one. But this difference does not determine how many individuals of the two species can be supported in a district. A large number of eggs is of some importance to those species which depend on a fluctuating amount of food, for it allows them to rapidly increase in number. But the real importance of a large number of eggs or seeds is to make up for much destruction at some period of life, and this period in the great majority of cases is an early one. If an animal can in any way protect its own eggs or young, a small number may be produced, and yet the average stock be fully kept up. But if many eggs or young are destroyed, many must be produced, or the species will become extinct. It would suffice to keep up the full number of a tree which lived on average for 1,000 years, if a single seed were produced once in 1,000 years, supposing that this seed were never destroyed and could be ensured to germinate in a fitting place. So that in all cases the average number of any animal or plant depends only indirectly on the number of its eggs or seeds. In looking at nature it is most necessary to keep the foregoing considerations always in mind, never to forget that every single organic being may be said to be striving to the utmost to increase their numbers, that each lives by a struggle at some period of its life, that heavy destruction inevitably falls either on the young or old during each generation or at recurrent intervals. Lighten any check, mitigate the destruction ever so little, and the number of the species will almost instantaneously increase to any amount. Nature of the checks to increase. The causes which check the natural tendency of each species to increase are most obscure. Look at the most vigorous species. By as much as it swarms in numbers, by so much it will tend to increase still further. We know not exactly what the checks are in a single instance, nor will this surprise any one who reflects on how ignorant we are on this head, even in regard to mankind, although so incomparably better known than any other animal. This subject of the checks to increase has been ably treated by several authors, and I hope in a future work to discuss it at considerable length, more especially in regard to the feral animals of South America. Here I will make only a few remarks, just to recall the reader's mind some of the chief points. Eggs or very young animals seem generally to suffer most, but this is not invariably the case. With plants there is a vast destruction of seeds, but from some observations which I have made it appears that the seedlings suffer most from germinating in ground already thickly stocked with other plants. Seedlings also are destroyed in vast numbers by various enemies. For instance, on a piece of ground 3 feet long and 2 wide, dug and cleared, where there could be no choking from other plants, I marked all the seedlings of our native weeds as they came up, and out of 357 no less than 295 were destroyed, chiefly by slugs and insects. If turf, which has long been mown, and the case would be the same with turf closely browsed by quadrupeds, be let to grow, the more vigorous plants gradually kill the less vigorous, though fully grown plants. Thus out of 20 species grown on a little plot of mown turf, 3 feet by 4, 9 species perished, from the other species being allowed to grow up freely. The amount of food for each species, of course, gives the extreme limit to which each can increase. But very frequently it is not the obtaining food, but the serving as prey to other animals, which determines the average number of a species. Thus there seems to be little doubt that the stock of partridges, grouse, and hares on any large estate depends chiefly on the destruction of vermin. If not one head of game were shot during the next 20 years in England, and, at the same time, if no vermin were destroyed, there would, in all probability, be less game than at present, although hundreds of thousands of game animals are now annually shot. On the other hand, in some cases, as with the elephant, none are destroyed by beasts of prey, for even the tiger in India most rarely dares to attack a young elephant protected by its dam. Climate plays an important part in determining the average numbers of a species, and periodical seasons of extreme cold or drought seem to be the most effective of all checks. I estimated, chiefly from the greatly reduced numbers of nests in the spring, that the winter of 1854-55 destroyed 4/5 of the birds in my own grounds, and this is a tremendous destruction when we remember that 10% is an extraordinarily severe mortality from epidemics with man. The action of climate seems at first sight to be quite independent of the struggle for existence, but in so far as climate chiefly acts in reducing food, it brings on the most severe struggle between the individuals, whether of the same distinct species, which subsist on the same kind of food. Even when climate, for instance, extreme cold, acts directly, it will be the least vigorous individuals, or those which have got least food through the advancing winter, which will suffer the most. When we travel from south to north, or from a damp region to a dry, we invariably see some species gradually getting rarer, and finally disappearing. And the change of climate being conspicuous, we are tempted to attribute the whole effect to its direct action. But this is a false view. We forget that each species, even where it most abounds, is constantly suffering enormous destruction at some period of its life, from enemies or from competitors for the same place and food. And if these enemies or competitors be in the least degree favored by any slight change of climate, they will increase in numbers. And as each area is already fully stocked with inhabitants, the other species must decrease. When we travel southward and see a species decreasing in numbers, we may feel sure that the cause lies quite as much in other species being favored as in this one being hurt. So it is when we travel northward, but in a somewhat lesser degree, for the number of species of all kinds, and therefore of competitors, decreases northwards. Hence in going northward, or in ascending a mountain, we far oftener meet with stunted forms, due to the directly injurious action of climate, than we do in proceeding southward or in descending a mountain. When we reach the Arctic regions, or snow-capped summits, or absolute deserts, the struggle for life is almost exclusively with the elements. That climate acts in main part indirectly by favouring other species, we clearly see in the prodigious number of plants which in our gardens can perfectly well endure our climate, but which never become naturalized, for they cannot compete with our native plants nor resist destruction by our native animals. When a species, owing to highly favourable circumstances, increases inordinately in numbers in a small tract, epidemics, at least this seems generally to occur with our game animals, often ensue. And here we have a limiting check, independent of the struggle for life. But even some of these so-called epidemics appear to be due to parasitic worms, which have from some cause, possibly in part through facility of diffusion among the crowded animals, been disproportionately favoured, and here comes in a sort of struggle between the parasite and its prey. On the other hand, in many cases a large stock of individuals of the same species, relatively to the numbers of its enemies, is absolutely necessary for its preservation. Thus we can easily raise plenty of corn and rapeseed, etc., in our fields, because the seeds are in great excess compared with the number of birds which feed on them. Nor can the birds, though having a superabundance of food at this one season, increase in number proportionately to the supply of seed, as their numbers are checked during the winter. But anyone who has tried knows how troublesome it is to get seed from a few wheat and other such plants in a garden. I have in this case lost every single seed. This view of the necessity of a large stock of the same species for its preservation explains, I believe, some singular facts in nature, such as that of very rare plants being sometimes extremely abundant in the few spots where they do exist, and that of some social plants being social, that is, abounding in individuals, even on the extreme verge of their range. For in such cases we may believe that a plant could exist only where the conditions of its life were so favourable that many could exist together, and thus save the species from utter destruction. I should add that the good effects of intercrossing and the ill effects of close inbreeding no doubt come into play in many of these cases, but I will not here enlarge on this subject. Complex relations of all animals and plants to each other in the struggle for existence. Many cases are on record showing how complex and unexpected are the checks and relations between organic beings which have to struggle together in the same country. I will give only a single instance which, though a simple one, interested me. In Staffordshire, on the estate of a relation, where I had ample means of investigation, there was a large and extremely barren heath, which had never been touched by the hand of man. But several hundred acres of exactly the same nature had been enclosed 25 years previously and planted with Scotch fir. The change in the native vegetation of the planted part of the heath was most remarkable, more than is generally seen in passing from one quite different soil to another. Not only the proportional numbers of the heath plants were wholly changed, but 12 species of plants, not counting grasses and carices, flourished in the plantations, which could not be found in the heath. The effect on the insects must have been still greater, for 6 insectivorous birds were very common in the plantations which were not to be seen on the heath, and the heath was frequented by 2 or 3 distinct insectivorous birds. Here we see how potent has been the effect of the introduction of a single tree, nothing whatever else having been done, with the exception of the land having been enclosed, so that cattle could not enter. But how important an element enclosure is, I plainly saw near Farnham in Surrey. Here there are extensive heaths, with a few clumps of old Scotch firs on the distant hilltops. Within the last 10 years large spaces have been enclosed, and self-sown firs are now springing up in multitudes, so close together that all cannot live. When I ascertained that these young trees had not been sown or planted, I was so much surprised at their numbers that I went to several points of view, whence I could examine hundreds of acres of the enclosed heath, and literally I could not see a single Scotch fir except the old planted clumps. But on looking closely between the stems of a heath, I found a multitude of seedlings and little trees, which had been perpetually browsed down by the cattle. In 1 square yard, at a point some 100 yards distant from the old clumps, I counted 32 little trees, and one of them, with 26 rings of growth, had, during many years, tried to raise its head above the stems of the heath, and had failed. No wonder that as soon as the land was enclosed it became thickly clothed with vigorously growing young firs. Yet the heath was so extremely barren and so extensive that no one would ever have imagined that cattle would have so closely and effectually searched it for food. Here we see that cattle absolutely determine the existence of the Scotch fir, but in several parts of the world insects determine the existence of cattle. Perhaps Paraguay offers the most curious instance of this, for here neither cattle nor horses nor dogs have ever run wild, though they swarm southward and northward in a feral state; and Azara and Reneger have shown that this is caused by the greater number in Paraguay of a certain fly which lays its eggs in the navels of these animals when first born. The increase of these flies, numerous as they are, must be habitually checked by some means, probably by other parasitic insects. Hence, if certain insectivorous birds were to decrease in Paraguay, the parasitic insects would probably increase, and this would lessen the number of the navel-frequenting flies. Then cattle and horses would become feral, and this would certainly greatly alter, as indeed I have observed in parts of South America, the vegetation. This again would largely affect the insects, and this, as we have just seen in Staffordshire, the insectivorous birds, and so onwards in ever-increasing circles of complexity. Not that under nature the relations will ever be as simple as this. Battle within battle must be continually recurring with varying success, and yet in the long run the forces are so nicely balanced that the face of nature remains for long periods of time uniform, though assuredly the merest trifle would give the victory to one organic being over another. Nevertheless, so profound is our ignorance and so high our presumption that we marvel when we hear of the extinction of an organic being, and as we do not see the cause, we invoke cataclysms to desolate the world, or invent laws on the duration of the forms of life. I am tempted to give one more instance showing how plants and animals, remote in the scale of nature, are bound together by a web of complex relations. I shall hereafter have occasion to show that the exotic Lobelia fulgens is never visited in my garden by insects, and consequently, from its particular structure, never sets a seed. Nearly all our orchidaceous plants absolutely require the visits of insects to remove their pollen masses and thus to fertilize them. I find from experiments that humble-bees are almost indispensable to the fertilization of the heartsease Viola tricolor, for other bees do not visit this flower. I have also found that the visits of bees are necessary for the fertilizations of some kinds of clover, for instance 20 heads of Dutch clover, Trifolium repens, yielded 2,290 seeds, but 20 other heads, protected from bees, produced not one. Again, 100 heads of red clover, T. pratans, produced 2,700 seeds, but the same number of protected heads produced not a single seed. Humble bees alone visited red clover, as other bees cannot reach the nectar. It has been suggested that moths may fertilize the clovers, but I doubt whether they could do so in the case of the red clover, from their weight not being sufficient to depress the wing petals. Hence we may infer as highly probable that, if the whole genus of humble-bees came extinct or very rare in England, the heartsease and red clover would become very rare or wholly disappear. The number of humble-bees in any district depends in a great measure upon the number of field mice which destroy their combs and nest, and Colonel Newman, who has long attended to the habits of humble-bees, believes that more than 2/3 of them are thus destroyed all over England. Now the number of mice is largely dependent, as everyone knows, on the number of cats. And Colonel Newman says, near villages and small towns I have found the nests of humble-bees more numerous than elsewhere, which I attribute to the number of cats that destroy the mice. Hence it is quite credible that the presence of a feline animal in large numbers in a district might determine, through the intervention first of mice and then of bees, the frequency of certain flowers in that district. In the case of every species, many different checks, acting at different periods of life and during different seasons of the year, probably come into play. Some one check, or some few being generally the most potent, but all will
concur in determining the average number or even the existence of species. In some cases it can be shown that widely different checks act on the same species in different districts. When we look at the plants and bushes clothing an entangled bank, we are tempted to attribute their proportional numbers and kinds to what we call chance. But how false a view is this! Everyone has heard that when an American forest is cut down, a very different vegetation springs up. But it has been observed that ancient Indian ruins in the southern United States, which must formerly have been cleared of trees, now display the same beautiful diversity and proportion of kinds as in the surrounding virgin forests. What a struggle must have gone on during long centuries between several kinds of trees, each annually scattering its seed by the thousand. What war between insect and insect, between insects, snails, and other animals, with birds and beasts of prey, all striving to increase, all feeding on each other, or on the trees, their seeds and seedlings, or on the other plants which first clothed the ground and thus checked the growth of trees. Throw up a handful of feathers, and all fall to the ground according to definite laws. But how simple is the problem of where each shall fall compared to that of the action and reaction of the innumerable plants and animals, which have determined in the course of centuries the proportional numbers and kinds of trees now growing on the old Indian ruins. The dependency of one organic being on another, as of parasite on its prey, lies generally between beings remote in the scale of nature. This is likewise sometimes the case with those which may strictly be said to struggle with each other for existence, as in the case of locusts and grass-feeding quadrupeds. But the struggle will almost invariably be most severe between the individuals of the same species, for they frequent the same districts, require the same food, and are exposed to the same dangers. In the case of varieties of the same species the struggle will generally be almost equally severe, and we sometimes see the contest soon decided. For instance, if several varieties of wheat be sown together, and the mixed seed be resown, some of the varieties which best suit the soil or climate, or are naturally the most fertile, will beat the others and so yield more seed, and will consequently, in a few years, supplant the other varieties. To keep up a mixed stock of even such extremely close varieties as the variously colored sweet peas, they must be each year harvested separately, and the seed then mixed in due proportion, otherwise the weaker kinds will steadily decrease in number and disappear. So again with the varieties of sheep. It has been asserted that certain mountain varieties will starve out other mountain varieties, so that they cannot be kept together. The same result has followed from keeping together different varieties of medicinal leech. It may even be doubted whether the varieties of any of our domestic plants or animals have so exactly the same strength, habits, and constitution that the original proportions of a mixed stock, crossing being prevented, could be kept up for half a dozen generations, if they were allowed to struggle together in the same manner as beings in a state of nature, and if the seed or young were not annually preserved in due proportion. Struggle for life most severe between individuals and varieties of the same species. As the species of the same genus usually have, though by no means invariably, much similarity in habits and constitution, and always in structure, the struggle will generally be more severe between them, if they come into competition with each other, than between the species of distinct genera. We see this in the recent extension over parts of the United States of one species of swallow having caused the decrease of another species. The recent increase of the missel thrush in parts of Scotland has caused the decrease of the song thrush. How frequently we hear of one species of rat taking the place of another species under the most different climates. In Russia the small Asiatic cockroach has everywhere driven before it its great congener. In Australia the imported hive bee is rapidly exterminating the small stingless native bee. One species of charlock has been known to supplant another species, and so in other cases. We can dimly see why the competition should be most severe between allied forms, which fill nearly the same place in the economy of nature, but probably in no one case could we precisely say why one species has been victorious over another in the great battle of life. The corollary of the highest importance may be deduced from the foregoing remarks, namely, that the structure of every organic being is related, in the most essential yet often hidden manner, to that of all other organic beings, with which it comes into competition for food or resilience, or from which it has to escape, or on which it preys. This is obvious in the structure of the teeth and talons of the tiger, and in that of the legs and claws of the parasite which clings to the hair of the tiger's body. But in the beautifully plumed seed of the dandelion, and in the flattened and fringed legs of the water beetle, the relation seems at first confined to the elements of air and water. Yet the advantage of the plumed seeds no doubt stands in the closest relation to the land being already thickly clothed with other plants, so that the seed may be widely distributed and fall on unoccupied ground. In the water beetle the structure of its legs, so well adapted for diving, allows it to compete with other aquatic insects, to hunt for its own prey, and to escape serving as prey to other animals. The store of nutriment laid up within the seeds of many plants seem at first sight to have no sort of relation to other plants, but from the strong growth of young plants produced from such seeds, as peas and beans, when sown in the midst of long grass, it may be suspected that the chief use of the nutriment in the seed is to favour the growth of the seedlings, whilst struggling with other plants growing vigorously all around. Look at a plant in the midst of its range. Why does it not double or quadruple its numbers? We know that it can perfectly well withstand a little more heat or cold, dampness or dryness, for elsewhere it ranges into slightly hotter or colder, damper or drier districts. In this case we can clearly see that if we wish in imagination to give the plant the power of increasing in numbers, we should have to give it some advantage over its competitors, or over the animals which prey on it. On the confines of its geographical range, a change of constitution with respect to climate would clearly be an advantage to our plant. But we have reason to believe that only a few plants or animals range so far that they are destroyed exclusively by the rigour of the climate. Not until we reach the extreme confines of life in the Arctic regions, or on the borders of an utter desert, will competition cease. The land may be extremely cold or dry, yet there will be competition between some few species or between the individuals of the same species for the warmest or dampest spots. Hence we can see that when a plant or animal is placed in a new country, among new competitors, the conditions of its life will generally be changed in an essential manner, although the climate may be exactly the same as in its former home. If its average numbers are to increase in its new home, we should have to modify it in a different way to what we should have had to do in its native country, for we should have to give it some advantage over a different set of competitors or enemies. It is good thus to try in imagination to give one species an advantage over another. Probably in no single instance should we know what to do. This ought to convince us of our ignorance on the mutual relations of all organic beings, a conviction necessary as it is difficult to acquire. All that we can do is keep steadily in mind that each organic being is striving to increase in a geometrical ratio, that each, at some period of its life, during some season of the year, during each generation, or at intervals, has to struggle for life and to suffer great destruction. When we reflect on this struggle, we may console ourselves with the full belief that the war of nature is not incessant, that no fear is felt, that death is generally prompt, and that the vigorous, the healthy, and the happy survive and multiply. End of chapter 3.
This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. The Origin of Species by Means of Natural Selection, or the Preservation of Favoured Races in the Struggle for Life. 6th London edition by Charles Darwin. Chapter number 4. Natural Selection, or the Survival of the Fittest. Section 1 of 3. Contents of this chapter include natural selection, its power compared with man's selection, its power on characters of trifling importance, its power at all ages and on both sexes. Sexual selection. On the generality of intercrosses between the individuals of the same species. Circumstances favourable and unfavourable to the results of natural selection, namely, intercrossing, isolation, number of individuals. Slow action. Extinction caused by natural selection. Diversity of character related to the diversity of inhabitants of any small area and to naturalization. Action of natural selection through divergence of character and extinction on the descendants from a common parent. Explains the grouping of all organic beings. Advance in organization. Low forms preserved. Convergence of character. Indefinite multiplication of species, and summary. How will the struggle for existence, briefly discussed in the last chapter, act in regard to variation? Can the principle of selection, which we have seen is so potent in the hands of man, apply under nature? I think we shall see that it can act most efficiently. Let the endless number of slight variations and individual differences occurring in our domestic productions, and in a lesser degree in those under nature, be borne in mind, as well as the strength of the hereditary tendency. Under domestication, it may truly be said that the whole organization becomes in some degree plastic. But the variability which we almost universally meet with in our domestic productions is not directly produced, as Hooker and Asa Gray have well remarked, by man. He can neither originate varieties nor prevent their occurrence. He can only preserve and accumulate such as do occur. Unintentionally, he exposes organic beings to new and changing conditions of life, and variability ensues. But similar changes of conditions might and do occur under nature. Let it also be borne in mind how infinitely complex and close-fitting are the mutual relations of all organic beings to each other and to their physical conditions of life, and consequently what infinitely varied diversities of structure might be of use to each being under changing conditions of life. Can it then be thought improbable, seeing that variations useful to man have undoubtedly occurred, that other variations useful in some way to each being in the great and complex battle of life should occur in the course of many successive generations? If such do occur, can we doubt, remembering that many more individuals are born than can possibly survive, that individuals having any advantage, however slight, over others, would have the best chance of surviving and procreating their kind? On the other hand, we may feel sure that any variation in the least degree injurious would be rigidly destroyed. This preservation of favourable individual differences and variations, and the destruction of those which are injurious, I have called natural selection, or the survival of the fittest. Variations neither useful nor injurious would not be affected by natural selection, and would be left either a fluctuating element, as perhaps we see in certain polymorphic species, or would ultimately become fixed, owing to the nature of the organism and the nature of the conditions. Several writers have misapprehended or objected to the term natural selection. Some have even imagined that natural selection induces variability, whereas it implies only the preservation of such variations as arise and are beneficial to the being under its conditions of life. No one objects to agriculturists speaking of the potent effects of man's selection, and in this case the individual differences given by nature, which man for some objects selects, must of necessity first occur. Others have objected that the term selection implies conscious choice in the animals which become modified, and it has even been urged that, as plants have no volition, natural selection is not applicable to them. In the literal sense of the word, no doubt, natural selection is a false term, but whoever objected to chemists speaking of the elective affinities of the various elements? And yet an acid cannot strictly be said to elect the base with which it in preference combines. It has been said that I speak of natural selection as an active power or deity. But who objects to an author speaking of the attraction of gravity as ruling the movements of the planets? Everyone knows what is meant and is implied by such metaphorical expressions, and they are almost necessary for brevity. So again, it is difficult to avoid personifying the word nature, and I mean by nature only the aggregate action and product of many natural laws, and by laws the sequence of events as ascertained by us. With a little familiarity, such superficial objections will be forgotten. We shall best understand the probable course of natural selection by taking the case of a country undergoing some slight physical change, for instance of climate. The proportional numbers of its inhabitants will almost immediately undergo a change, and some species will probably become extinct. We may conclude, from what we have seen of the intimate and complex manner in which the inhabitants of each country are bound together, that any change in the numerical proportions of the inhabitants, independently of the change of climate itself, would seriously affect the others. If the country were open on its borders, new forms would certainly immigrate, and this would likewise seriously disturb the relations of some of the former inhabitants. Let it be remembered how powerful the influence of a single introduced tree or mammal has been shown to be. But in the case of an island, or of a country partly surrounded by barriers, into which new and better adapted forms could not freely enter, we should then have places in the economy of nature which would assuredly be better filled up if some of the original inhabitants were in some manner modified. For had the area been open to immigration, these same places would have been seized on by intruders. In such cases, slight modifications which in any way favoured the individuals of any species, by better adapting them to their altered conditions, would tend to be preserved, and natural selection would have free scope for the work of improvement. We have good reason to believe, as shown in the first chapter, that changes in the conditions of life give a tendency to increased variability, and in the foregoing cases the conditions changed, and this would manifestly be favourable to natural selection, by affording a better chance of the occurrence of profitable variations. Unless such occur, natural selection can do nothing. Under the term of variations, it must never be forgotten that mere individual differences are included. As man can produce a great result with his domestic animals and plants by adding up in any given direction individual differences, so could natural selection, but far more easily from having incomparably longer time for action. Nor do I believe that any great physical change, as of climate, or any unusual degree of isolation to check immigration, is necessary in order that new and unoccupied places should be left for natural selection to fill up by improving some of the varying inhabitants. For as all the inhabitants of each country are struggling together with nicely balanced forces, extremely slight modifications in the structure or habits of one species would often give it an advantage over others, and still further modifications of the same kind would often still further increase the advantage, as long as the species continued under the same conditions of life and profited by similar means of subsistence and defence. No country can be named in which all the native inhabitants are now so perfectly adapted to each other and to the physical conditions under which they live, that none of them could be still better adapted or improved. For in all countries the natives have been so far conquered by naturalised productions that they have allowed some foreigners to take firm possession of the land. And as foreigners have thus in every country beaten some of the natives, we may safely conclude that the natives might have been modified with advantage, so as to have better resisted the intruders. As man can produce, and certainly has produced, a great result by his methodical and unconscious means of selection, what may not natural selection effect? Man can act only on external and visible characters. Nature, if I may be allowed to personify the natural preservation or survival of the fittest, cares nothing for appearances, except in so far as they are useful to any being. She can act on every internal organ, on every shade of constitutional difference, on the whole machinery of life. Man selects only for his own good, nature only for that of the being which she tends. Every selected character is fully exercised by her, as is implied by the fact of their selection. Man keeps the natives of many climates in the same country. He seldom exercises each selected character in some peculiar and fitting manner. He feeds a long and a short-beaked pigeon on the same food. He does not exercise a long-backed or long-legged quadruped in any particular manner. He exposes sheep with long and short wool to the same climate, does not allow the most vigorous males to struggle for the females. He does not rigidly destroy all inferior animals, but protects during each varying season, as far as lies in his power, all his productions. He often begins his selection by some half-monstrous form, or at least by some modification prominent enough to catch the eye, or to be plainly useful to him. Under nature, the slightest differences of structure or constitution may well turn the nicely balanced scale in the struggle for life, and so be preserved. How fleeting are the wishes and efforts of man! How short his time, and consequently how poor will be his results, compared with those accumulated by nature during whole geological periods. Can we wonder then that nature's productions should be far truer in character than man's productions, that they should be infinitely better adapted to the most complex conditions of life, and should plainly bear the stamp of far higher workmanship? It may metaphorically be stated that natural selection is daily and hourly scrutinizing throughout the world the slightest variations, rejecting those that are bad, preserving and adding up all that are good, silently and insensibly working, whenever and wherever opportunity offers, at the improvement of each organic being in relation to its organic and inorganic conditions of life. We see nothing of these slow changes in progress, until the hand of time has marked the long lapse of ages, and then so imperfect is our view into long past geological ages, that we see only that the forms of life are now different from what they formerly were. In order that any great amount of modification should be effected in a species, a variety, when once formed, must again, perhaps after a long interval of time, vary, or present individual differences of the same favourable nature as before, and these must again be preserved, and so onward, step by step. Seeing that individual differences of the same kind perpetually recur, this can hardly be considered as an unwarrantable assumption. But whether it is true, we can judge only by seeing how far the hypothesis occurs with and explains the general phenomena of nature. On the other hand, the ordinary belief that the amount of possible variation is a strictly limited quantity is likewise a simple assumption. Although natural selection can act only through and for the good of each being, yet characters and structures, which we are apt to consider as of very trifling importance, may thus be acted on. When we see leaf-eating insects green, and bark-feeders mottled grey, the alpine ptarmigan white in winter, the red grouse the colour of heather, we must believe that these tints are of service to these birds and insects in preserving them from danger. Grouse, if not destroyed at some period of their lives, would increase in countless numbers. They are known to suffer largely from birds of prey, and hawks are guided by eyesight to their prey. So much so, that on parts of the continent persons are warned not to keep white pigeons, as being the most liable to destruction. Hence natural selection might be effective in giving the proper colour to each kind of grouse, and in keeping that colour, when once required, true and constant. Nor ought we to think that the occasional destruction of an animal of any particular colour would produce little effect. We should remember how essential it is, in a flock of white sheep, to destroy a lamb with the faintest trace of black. We have seen how the colour of hogs, which feed on the paint root in Virginia, determines whether they shall live or die. In plants, the down on the fruit and the colour of the flesh are considered by botanists as characters of the most trifling importance. Yet we hear from an excellent horticulturist, Downing, that in the United States, smooth-skinned fruits suffer far more from a beetle, a curculio, than those with down; that purple plums suffer far more from a certain disease than yellow plums, whereas another disease attacks yellow-fleshed peaches far more than those with other coloured flesh. If, with all the aids of art, these slight differences make a great difference in cultivating the several varieties, assuredly in a state of nature, where the trees would have to struggle with other trees and with a host of enemies, such differences would effectually settle which variety, whether a smooth or downy, a yellow or a purple-fleshed fruit, should succeed. In looking at many small points of difference between species, which, as far as our ignorance permits us to judge, seem quite unimportant, we must not forget that climate, food, etc., have no doubt produced some direct effect. It is also necessary to bear in mind that, owing to the law of correlation, when one part varies and the variations are accumulated through natural selection, other modifications, often of the most unexpected nature, will ensue. As we see that those variations which, under domestication, appear at any particular period of life, tend to reappear in the offspring at the same period, for instance, in the shape, size and flavour of the seeds of the many varieties of our culinary and agricultural plants, in the caterpillar and cocoon stages of the varieties of the silkworm, in the eggs of poultry and in the colour of the down of their chickens, in the horns of our sheep and cattle when nearly adult. So, in a state of nature, natural selection will be enabled to act on and modify organic beings at any age, by the accumulation of variations profitable at that age, and by their inheritance at a corresponding age. If it profit a plant to have its seeds more and more widely disseminated by the wind, I can see no greater difficulty in this being effected through natural selection than in the cotton planter increasing and improving by selection the down in the pods on his cotton trees. Natural selection may modify and adapt the larva of an insect to a score of contingencies, wholly different from those which concern the mature insect. And these modifications may affect, through correlation, the structure of the adult. So, conversely, modifications in the adult may affect the structure of the larva. But in all cases, natural selection will ensure that they shall not be injurious, for if they were so, the species would become extinct. Natural selection will modify the structure of the young in relation to the parent, and of the parent in relation to the young. In social animals, it will adapt the structure of each individual for the benefit of the whole community, if the community profits by the selected change. What natural selection cannot do is to modify the structure of one species without giving it any advantage for the good of another species, and though statements to this effect may be found in works of natural history, I cannot find one case which will bear investigation. A structure used only once in an animal's life, if of high importance to it, might be modified to any extent by natural selection. For instance, the great jaws possessed by certain insects, used exclusively for opening the cocoon, or the hard tip to the beak of unhatched birds, used for breaking the eggs. It has been asserted that of the best short-beaked tumbler pigeons, a greater number perish in the egg than are able to get out of it, so that fanciers assist in the act of hatching. Now, if nature had to make the beak of a full-grown pigeon very short for the bird's own advantage, the process of modification would be very slow, and there would be simultaneously the most rigorous selection of all the young birds within the egg, which had the most powerful and hardest beaks. For all with weak beaks would inevitably perish, or more delicate and more easily broken shells might be selected, the thickness of the shell being known to vary like every other structure. It may be well here to remark that with all beings there must be much fortuitous destruction, which can have little or no influence on the course of natural selection. For instance, a vast number of eggs or seeds are annually devoured, and these could be modified through natural selection only if they varied in some manner which protected them from their enemies. Yet many of these eggs or seeds would perhaps, if not destroyed, have yielded individuals better adapted to their conditions of life than any of those which happened to survive. So again, a vast number of mature animals and plants, whether or not they be the best adapted to their conditions, must be annually destroyed by accidental causes, which would not be in the least degree mitigated by certain changes of structure or constitution, which would in other ways be beneficial to the species. But let the destruction of the adults be ever so heavy, if the number which can exist in any district be not wholly kept down by such causes, or again, let the destruction of eggs or seeds be so great that only 100th or 1,000th part are developed, yet of those which do survive, the best adapted individuals, supposing that there is any variability in a favourable direction, will tend to propagate their kind in larger numbers than the less well adapted. If the numbers be wholly kept down by the causes just indicated, as will often have been the case, natural selection will be powerless in certain beneficial directions. But this is no valid objection to its efficiency at other times and in other ways, for we are far from having any reason to suppose that many species ever undergo modification and improvement at the same time in the same area. Sexual selection. Inasmuch as peculiarities often appear under domestication in one sex and become hereditarily attached to that sex, so no doubt it will be under nature. Thus it is rendered possible for the two sexes to be modified through natural selection in relation to different habits of life, as is sometimes the case, or for one sex to be modified in relation to the other sex, as commonly occurs. This leads me to say a few words on what I have called sexual selection. This form of selection depends, not on a struggle for existence in relation to other organic beings or to external conditions, but on a struggle between the individuals of one sex, generally the males, for the possession of the other sex. The result is not death to the unsuccessful competitor, but few or no offspring. Sexual selection is therefore less rigorous than natural selection. Generally, the most vigorous males, those which are best fitted for their places in nature, will leave most progeny. But in many cases, victory depends not so much on general vigour, but on having special weapons confined to the male sex. A hornless stag or spurless cock would have a poor chance of leaving numerous offspring. Sexual selection, by always allowing the victor to breed, might surely give indomitable courage, length of spur, and strength to the wing to strike in the spurred leg, in nearly the same manner as does the brutal cockfighter by the careful selection of his best cocks. How low in the scale of nature the law of battle descends, I know not. Male alligators have been described as fighting, bellowing and whirling around, like Indians in a war dance, for the possession of the females. Male salmons have been observed fighting all day long. Male stag beetles sometimes bear wounds from the huge mandibles of other males. The males of certain hymenopterous insects have been frequently seen by that inimitable observer, M. Fabre, fighting for a particular female, who sits by, an apparently unconcerned beholder of the struggle, and then retires with the conqueror. The war is, perhaps, severest between the males of polygamous animals, and these seem oftenest provided with special weapons. The males of carnivorous animals are already well armed, though to them and to others special means of defence may be given through means of sexual selection, as the mane of the lion and the hooked jaw to the male salmon, for the shield may be as important for victory as the sword or spear. Among birds, the contest is often of a more peaceful character. All those who have attended to the subject believe that there is the severest rivalry between the males of many species to attract by singing the females. The rock thrush of Guyana, birds of paradise, and some others congregate, and successive males display with the most elaborate care and show off in the best manner their gorgeous plumage. They likewise perform strange antics before the females, which, standing by as spectators, at last choose the most attractive partner. Those who have closely attended to birds in confinement will know that they often take individual preferences and dislikes. Thus Sir R. Heron has described how a pied peacock was eminently attractive to all his hen birds. I cannot here enter on the necessary details, but if man can in a short time give beauty and an elegant carriage to his bantams, according to his standard of beauty, I can see no good reason to doubt that female birds, by selecting, during thousands of generations, the most melodious or beautiful males, according to their standard of beauty, might produce a marked effect. Some well-known laws, with respect to the plumage of male and female birds, in comparison with the plumage of the young, can partly be explained through the action of sexual selection on variations occurring at different ages, and transmitted to the males alone, or to both sexes at corresponding ages. But I have not space here to enter on this subject. Thus it is, as I believe, that when the males and females of any animal have the same general habits of life, but differ in structure, colour, or ornament, such differences have been mainly caused by sexual selection, that is, by individual males having had, in successive generations, some slight advantage over other males, in their weapons, means of defence, or charms, which they have transmitted to their male offspring alone. Yet I would not wish to attribute all sexual differences to this agency, for we see in our domestic animals peculiarities arising and becoming attached to the male sex, which apparently have not been augmented through selection by man. The tuft of hair on the breast of the wild turkey-cock cannot be of any use, and it is doubtful whether it can be ornamental in the eyes of the female bird. Indeed, had the tuft appeared under domestication, it would have been called a monstrosity. Illustrations of the action of natural selection, or the survival of the fittest. In order to make it clear how, as I believe, natural selection acts, I must beg permission to give one or two imaginary illustrations. Let us take the case of a wolf, which preys on various animals, securing some by craft, some by strength, and some by fleetness. And let us suppose that the fleetest prey, a deer for instance, had from any change in the country increased in numbers, or that other prey had decreased in numbers during that season of the year when the wolf was hardest pressed for food. Under such circumstances, the swiftest and slimmest wolves have the best chance of surviving, and so be preserved or selected, provided always that they retained strength to master their prey at this or some other period of the year, when they were compelled to prey on other animals. I can see no more reason to doubt that this would be the result, than that man should be able to improve the fleetness of his greyhounds by careful and methodical selection, or by that kind of unconscious selection which follows from each man trying to keep the best dogs, without any thought of modifying the breed. I may add that, according to Mr. Pearce, there are 2 varieties of the wolf inhabiting the Catskill Mountains in the United States, one with a light greyhound-like form which pursues deer, and the other more bulky, with shorter legs, which more frequently attacks the shepherd's flocks. Even without any change in the proportional numbers of the animals on which our wolf preyed, a cub might be born with an innate tendency to pursue certain kinds of prey. Nor can this be thought very improbable, for we often observe great differences in the natural tendencies of our domestic animals, one cat, for instance, taking to catching rats, another mice; one cat, according to Mr. St. John, bringing home winged game, another hares or rabbits, and another hunting on marshy ground, and almost nightly catching woodcocks or snipes. The tendency to catch rats rather than mice is known to be inherited. Now, if any slight innate change of habit or of structure benefited an individual wolf, it would have the best chance of surviving and of leaving offspring. Some of its young would probably inherit the same habits or structure, and by the repetition of this process, a new variety might be formed, which would either supplant or coexist with the parent form of wolf. Or, again, the wolves inhabiting a mountainous district and those frequenting the lowlands would naturally be forced to hunt different prey, and from the continued preservation of the individuals best fitted for the 2 sites, 2 varieties might slowly be formed. These varieties would cross and blend where they met, but to this subject of intercrossing we shall soon have to return. It should be observed that in the above illustration I speak of the slimmest individual wolves, and not of any single strongly marked variation having been preserved. In former editions of this work I sometimes spoke as if this latter alternative had frequently occurred. I saw the great importance of individual differences, and this led me fully to discuss the results of unconscious selection by man, which depends on the preservation of all the more or less valuable individuals, and on the destruction of the worst. I saw also that the preservation in a state of nature of any occasional deviation of structure, such as a monstrosity, would be a rare event, and that, if at first preserved, it would generally be lost by subsequent intercrossing with ordinary individuals. Nevertheless, until reading an able and valuable article in the North British Review, 1867, I did not appreciate how rarely single variations, whether slight or strongly marked, could be perpetuated. The author takes the case of a pair of animals producing during their lifetime 200 offspring, of which, from various causes of destruction, only 2 on an average survive to procreate their kind. This is rather an extreme estimate for most of the higher animals, but by no means so for many of the lower organisms. He then shows that if a single individual were born which varied in some manner, giving it twice as good a chance of life as that of the other individuals, yet the chances would be strongly against its survival. Supposing it to survive and to breed, and that half its young inherited the favourable variation, still, as the reviewer goes on to show, the young would have only a slightly better chance of surviving and breeding, and this chance would go on decreasing in the succeeding generations. The justice of these remarks cannot, I think, be disputed. If, for instance, a bird of some kind could procure its food more easily by having its beak curved, and if one were born with its beak strongly curved, and which consequently flourished, nevertheless there would be a very poor chance of this one individual perpetuating its kind to the exclusion of the common form. But there can hardly be a doubt, judging by what we see taking place under domestication, that this result would follow from the preservation during many generations of a large number of individuals with more or less strongly curved beaks, and from the destruction of a still larger number with the straightest beaks. It should not, however, be overlooked that certain rather strongly marked variations, which no one would rank as mere individual differences, frequently recur owing to a similar organisation being similarly acted on, of which fact numerous instances could be given with our domestic productions. In such cases, if the varying individual did not actually transmit to its offspring its newly acquired character, it would undoubtedly transmit to them, as long as the existing conditions remained the same, a still stronger tendency to vary in the same manner. There can also be little doubt that the tendency to vary in the same manner has often been so strong that all the individuals of the same species have been similarly modified without the aid of any form of selection, or only a third, fifth, or 10th part of the individuals may have been thus affected, of which fact several instances could be given. Thus Graber estimates that about 1/5 of the guillemots in the Faroe Islands consist of a variety so well marked that it was formerly ranked as a distinct species under the name of Urea lacrymans. In cases of this kind, if the variation were of a beneficial nature, the original form would soon be supplanted by the modified form, through the survival of the fittest. To the effects of intercrossing in eliminating variations of all kinds I shall have to recur, but it may be here remarked that most animals and plants keep to their proper homes, and do not needlessly wander about. We see this even with migratory birds, which almost always return to the same spot. Consequently, each newly formed variety would generally be at first local, as seems to be the common rule with varieties in a state of nature, so that similarly modified individuals would soon exist in a small body together, and would often breed together. If the new variety were successful in its battle for life, it would slowly spread from a central district, competing with and conquering the unchanged individuals on the margins of an ever-increasing circle. It may be worth while to give another and more complex illustration of the action of natural selection. Certain plants excrete sweet juice, apparently for the sake of eliminating something injurious from the sap. This is effected, for instance, by glands at the base of the stipules in some leguminosæ, and at the backs of the leaves of the common laurel. This juice, though small in quantity, is greedily sought by insects, but their visits do not in any way benefit the plant. Now, let us assume that the juice or nectar was excreted from the inside of the flowers of a certain number of plants of any species. Insects, in seeking the nectar, would get dusted with pollen, and would often transport it from one flower to another. The flowers of two distinct individuals of the same species would thus get crossed, and the act of crossing, as can be fully proved, gives rise to vigorous seedlings, which consequently would have the best chance of flourishing and surviving. The plants which produced flowers with the largest glands or nectaries, excreting most nectar, would oftenest be visited by insects, and would oftenest be crossed, and so, in the long run, would gain the upper hand and form a local variety. The flowers also which had their stamens and pistils placed, in relation to the size and habits of the particular insect which visited them, so as to favour in any degree the transportal of the pollen, would likewise be favoured. We might have taken the case of insects visiting flowers for the sake of collecting pollen instead of nectar, and as pollen is formed for the sole purpose of fertilisation, its destruction appears to be a simple loss to the plant. Yet if a little pollen were carried, at first occasionally and then habitually, by the pollen-devouring insects from flower to flower, and a cross thus effected, although 9/10 of the pollen were destroyed, it might still be a great gain to the plant to be thus robbed, and the individuals which produced more and more pollen and had larger anthers would be selected. When our plant, by the above process long continued, had been rendered highly attractive to insects, they would, unintentionally on their part, regularly carry pollen from flower to flower, and that they do this effectually I could easily show by many striking facts. I will give only one, as likewise illustrating one step in the separation of the sexes of plants. Some holly trees bear only male flowers, which have 4 stamens, producing a rather small quantity of pollen, and a rudimentary pistil. Other holly trees bear only female flowers. These have a full-sized pistil, and 4 stamens with shrivelled anthers, in which not a grain of pollen can be detected. Having found a female tree, exactly 60 yards from a male tree, I put the stigmas of 20 flowers, taken from different branches, under the microscope, and on all, without exception, there were a few pollen grains, and on some a profusion. As the wind had set for several days from the female to the male tree, the pollen could not thus have been carried. The weather had been cold and boisterous, and therefore not favourable to bees. Nevertheless, every female flower which I examined had been effectually fertilised by the bees, which had flown from tree to tree in search of nectar. But to return to our imaginary case, as soon as the plant had been rendered so highly attractive to insects that pollen was regularly carried from flower to flower, another process might commence. No naturalist doubts the advantage of what has been called the physiological division of labour. Hence we may believe that it would be advantageous to a plant to produce stamens alone in one flower, or on one whole plant, and pistils alone in another flower, or on another plant. In plants under culture, and placed under new conditions of life, sometimes the male organs and sometimes the female organs become more or less impotent. Now, if we suppose this to occur in ever so slight a degree under nature, then, as pollen is already carried regularly from flower to flower, and as a more complete separation of the sexes of our plant would be advantageous, on the principle of the division of labour, individuals with this tendency more and more increased would be continually favoured or selected, until at last a complete separation of the sexes might be effected. it would take up too much space to show the various steps, through dimorphism and other means, by which the separation of the sexes in plants of various kinds is apparently now in progress, but I may add that some of the species of holly in North America are, according to Asa Gray, in an exactly intermediate condition, or, as he expresses it, are more or less dioeciously polygamous. Let us now turn to the nectar-feeding insects. We may suppose the plant of which we have been slowly increasing the nectar by continued selection to be a common plant, and that certain insects depended in part on its nectar for food. I could give many facts showing how anxious bees are to save time. For instance, their habit of cutting holes and sucking the nectar at the bases of certain flowers, which with a very little more trouble they can enter by the mouth. Bearing such facts in mind, it may be believed that under certain circumstances individual differences in the curvature or length of the proboscis, etc., too slight to be appreciated by us, might benefit a bee or other insect, so that certain individuals would be able to obtain their food more quickly than others, and thus the communities to which they belonged would flourish and throw off many swarms inheriting the same peculiarities. The tubes of the corolla of the common red or incarnate clovers, Trifolium pratense and incarnatum, do not on a hasty glance appear to differ in length, yet the hive bee can easily suck the nectar out of the incarnate clover, but not out of the common red clover, which is visited by humble bees alone, so that whole fields of the red clover offer in vain an abundant supply of precious nectar to the hive bee. That this nectar is much liked by the hive bee is certain, for I have repeatedly seen, but only in the autumn, many hive bees sucking the flowers through holes bitten in the base of the tube by humble bees. The difference in the length of the corolla in the two kinds of clover, which determines the visits of the hive bee, must be very trifling, for I have been assured that when red clover has been mown, the flowers of the second crop are somewhat smaller, and that these are visited by many hive bees. I do not know whether this statement is accurate, nor whether another published statement can be trusted, namely, that the Ligurian bee, which is generally considered a mere variety of the common hive bee, and which freely crosses with it, is able to reach and suck the nectar of the red clover. Thus, in a country where this kind of clover abounded, it might be a great advantage to the hive bee to have a slightly longer or differently constructed proboscis. On the other hand, as the fertility of this clover absolutely depends on bees visiting the flowers, if humble bees were to become rare in any country, it might be a great advantage to the plant to have a shorter or more deeply divided corolla, so that the hive bees should be enabled to suck its flowers. Thus I can understand how a flower and a bee might slowly become, either simultaneously or one after the other, modified and adapted to each other in the most perfect manner, by the continued preservation of all the individuals which presented slight deviations of structure mutually favourable to each other. I am well aware that this doctrine of natural selection, exemplified in the above imaginary instances, is open to the same objections which were first urged against Sir Charles Lyell's noble views on the modern changes of the earth, as illustrative of geology, but we now seldom hear the agencies which we still see at work spoken of as trifling and insignificant, when used in explaining the excavation of the deepest valleys, or the formation of long lines of inland cliffs. Natural selection acts only by the preservation and accumulation of small inherited modifications, each profitable to the preserved being, and as modern geology has almost banished such views as the excavation of a great valley by a single diluvial wave, so will natural selection banish the belief of the continued creation of new organic beings, or of any great and sudden modification in their structure. End of section 1 of chapter 4. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. The origin of species by means of natural selection, or the preservation of favoured races in the struggle for life. 6th London edition by Charles Darwin. Chapter number 4. Natural selection, or the survival of the fittest. Section 2 of 3. On the intercrossing of individuals. I must here introduce a short digression. In the case of animals and plants with separated sexes, it is of course obvious that two individuals must always, with the exception of the curious and not well understood cases of parthenogenesis, unite for each birth. But in the case of hermaphrodites, this is far from obvious. Nevertheless, there is reason to believe that with all hermaphrodites, two individuals, either occasionally or habitually, concur for the reproduction of their kind. This view was long ago doubtfully suggested by Sprengel, Knight and Kölreuter. We shall presently see its importance, but I must here treat the subject with extreme brevity, though I have the materials prepared for an ample discussion. All vertebrate animals, all insects, and some other large groups of animals, pair for each birth. Modern research has much diminished the number of supposed hermaphrodites, and of real hermaphrodites a large number pair. That is, two individuals regularly unite for reproduction, which is all that concerns us. But still there are many hermaphrodite animals which certainly do not habitually pair, and a vast majority of plants are hermaphrodites. What reason, it may be asked, is there for supposing in these cases that two individuals ever concur in reproduction? As it is impossible here to enter on details, I must trust to some general considerations alone. In the first place, I have collected so large a body of facts, and made so many experiments, showing, in accordance with the almost universal belief of breeders, that with animals and plants, a cross between different varieties, or between individuals of the same variety but of another strain, gives vigour and fertility to the offspring, and on the other hand, that close interbreeding diminishes vigour and fertility. That these facts alone incline me to believe that it is a general law of nature that no organic being fertilizes itself for a perpetuity of generations, but that a cross with another individual is occasionally, perhaps at long intervals of time, indispensable. On the belief that this is a law of nature, we can, I think, understand several large classes of facts, such as the following, which on any other view are inexplicable. Every hybridizer knows how unfavourable exposure to wet is to the fertilization of a flower. Yet what a multitude of flowers have their anthers and stigmas fully exposed to the weather. if an occasional cross be indispensable, notwithstanding that the plant's own anthers and pistil stand so near each other as almost to ensure self-fertilisation, the fullest freedom for the entrance of pollen from another individual will explain the above state of exposure of the organs. Many flowers, on the other hand, have their organs of fructification closely enclosed, as in the great Papilionaceous or pea family, but these almost invariably present beautiful and curious adaptations in relation to the visits of insects. So necessary are the visits of bees to many papilionaceous flowers that their fertility is greatly diminished if these visits be prevented. Now it is scarcely possible for insects to fly from flower to flower and not to carry pollen from one to the other, to the great good of the plant. Insects act like a camel hair pencil, and it is sufficient to ensure fertilisation just to touch with the same brush the anthers of one flower and then the stigma of another. But it must not be supposed that bees would thus produce a multitude of hybrids between distinct species. For if a plant's own pollen and that from another species are placed on the same stigma, the former is so prepotent that it invariably and completely destroys, as has been shown by Gärtner, the influence of the foreign pollen. When the stamens of a flower suddenly spring towards the pistil, or slowly move one after the other towards it, the contrivance seems adapted solely to ensure self-fertilisation, and no doubt it is useful for this end. But the agency of insects is often required to cause the stamens to spring forward, as Kölreuter has shown to be the case with the barberry. And in this very genus, which seems to have a special contrivance for self-fertilisation, it is well known that, if closely allied forms or varieties are planted near each other, it is hardly possible to raise pure seedlings, so largely do they naturally cross. In numerous other cases, far from self-fertilisation being favoured, there are special contrivances which effectually prevent the stigma receiving pollen from its own flower, as I could show from the works of Sprengel and others, as well as from my own observations. For instance, in Lobelia fulgens there is a really beautiful and elaborate contrivance by which all the infinitely numerous pollen granules are swept out of the conjoined anthers of each flower, before the stigma of that individual flower is ready to receive them. And as this flower is never visited, at least in my garden, by insects, it never gets a seed, though by placing pollen from one flower on the stigma of another, I raise plenty of seedlings. Another species of Lobelia, which is visited by bees, seeds freely in my garden. In very many other cases, though there is no special mechanical contrivance to prevent the stigma receiving pollen from the same flower, yet, as Sprengel and more recently Hildebrand and others have shown, and as I can confirm, either the anthers burst before the stigma is ready for fertilisation, or the stigma is ready before the pollen of that flower is ready, so that these so-named dichogamous plants have in fact separated sexes, and must habitually be crossed. So it is with the reciprocally dimorphic and trimorphic plants previously alluded to. How strange are these facts! How strange that the pollen and stigmatic surface of the same flower, though placed so close together, as if for the very purpose of self-fertilisation, should be in so many cases mutually useless to each other. How simply are these facts explained, on the view of an occasional cross with a distinct individual being advantageous or indispensable. If several varieties of the cabbage, radish, onion, and of some other plants be allowed to seed near each other, a large majority of the seedlings thus raised turn out, as I found, mongrels. For instance, I raised 233 seedling cabbages from some plants of different varieties growing near each other, and of these only 78 were true to their kind, and some even of these were not perfectly true. Yet the pistil of each cabbage flower is surrounded not only by its own 6 stamens, but by those of the many other flowers on the same plant, and the pollen of each flower readily gets on its stigma without insect agency, for I have found that plants carefully protected from insects produce the full number of pods. How then comes it that such a vast number of the seedlings are mongrelized? It must arise from the pollen of a distinct variety having a prepotent effect over the flower's own pollen, and that this is part of the general law of good being derived from the intercrossing of distinct individuals of the same species. When distinct species are crossed, the case is reversed, for a plant's own pollen is always prepotent over foreign pollen. But to this subject we shall return in a future chapter. In the case of a large tree covered with innumerable flowers, it may be objected that pollen could seldom be carried from tree to tree, and at most only from flower to flower on the same tree, and flowers on the same tree can be considered as distinct individuals only in a limited sense. I believe this objection to be valid, but that nature has largely provided against it by giving to trees a strong tendency to bear flowers with separated sexes. When the sexes are separated, although the male and female flowers may be produced on the same tree, pollen must be regularly carried from flower to flower, and this will give a better chance of pollen being occasionally carried from tree to tree. That trees belonging to all orders have their sexes more often separated than other plants, I find to be the case in this country, and at my request Dr. Hooker tabulated the trees of New Zealand, and Dr. Asa Gray those of the United States, and the result was as I anticipated. On the other hand, Dr. Hooker informs me that the rule does not hold good in Australia. But if most of the Australian trees are dichogamous, the same result will follow as if they bore flowers with separated sexes. I have made these few remarks on trees simply to call attention to the subject. Turning for a brief space to animals, various terrestrial species are hermaphrodites, such as the land mollusca and earthworms, but these all pair. As yet I have not found a single terrestrial animal which can fertilize itself. This remarkable fact, which offers so strong a contrast with terrestrial plants, is intelligible on the view of an occasional cross being indispensable. For owing to the nature of the fertilizing element, there are no means, analogous to the action of insects and of the wind with plants, by which an occasional cross could be effected with terrestrial animals without the concurrence of two individuals. Of aquatic animals there are many self-fertilizing hermaphrodites, but here the currents of water offer an obvious means for an occasional cross. As in the case of flowers, I have as yet failed, after consultation with one of the highest authorities, namely Professor Huxley, to discover a single hermaphrodite animal with the organs of reproduction so perfectly enclosed that access from without, and the occasional influence of a distinct individual, can be shown to be physically impossible. Cirripedes long appeared to me to present, under this point of view, a case of great difficulty, but I have been enabled, by a fortunate chance, to prove that two individuals, though both are self-fertilizing hermaphrodites, do sometimes cross. It must have struck most naturalists as a strange anomaly that, both with animals and plants, some species of the same family, and even of the same genus, though agreeing closely with each other in their whole organization, are hermaphrodites, and some unisexual. But if, in fact, all hermaphrodites do occasionally intercross, the difference between them and unisexual species is, as far as function is concerned, very small. From these several considerations, and from the many special facts which I have collected, but which I am unable here to give, it appears that with animals and plants an occasional intercross between distinct individuals is a very general, if not universal, law of nature. Circumstances favourable for the production of new forms through natural selection. This is an extremely intricate subject. A great amount of variability, under which term individual differences are always included, will evidently be favourable. A large number of individuals, by giving a better chance within any given period for the appearance of profitable variations, will compensate for a lesser amount of variability in each individual, and is, I believe, a highly important element of success. Though nature grants long periods of time for the work of natural selection, she does not grant an indefinite period. For as all organic beings are striving to seize on each place in the economy of nature, if any one species does not become modified and improved in a corresponding degree with its competitors, it will be exterminated. Unless favourable variations be inherited by some at least of the offspring, nothing can be effected by natural selection. The tendency to reversion may often check or prevent the work, but as this tendency has not prevented man from forming by selection numerous domestic races, why should it prevail against natural selection? In the case of methodical selection, a breeder selects for some definite object, and if the individuals be allowed freely to intercross, his work will completely fail. But when many men, without intending to alter the breed, have a nearly common standard of perfection, and all try to procure and breed from the best animals, improvement surely but slowly follows from this unconscious process of selection, notwithstanding that there is no separation of selected individuals. Thus it will be under nature. For within a confined area, with some place in the natural polity not perfectly occupied, all the individuals varying in the right direction, though in different degrees, will tend to be preserved. But if the area be large, its several districts will almost certainly present different conditions of life, and then, if the same species undergoes modification in different districts, the newly formed varieties will intercross on the confines of each. But we shall see in the 6th chapter that intermediate varieties, inhabiting intermediate districts, will in the long run generally be supplanted by one of the adjoining varieties. Intercrossing will chiefly affect those animals which unite for each birth and wander much, and which do not breed at a very quick rate. Hence with animals of this nature, for instance birds, varieties will generally be confined to separate countries, and this I find to be the case. With hermaphrodite organisms which cross only occasionally, and likewise with animals which unite for each birth but which wander little and can increase at a rapid rate, a new and improved variety might be quickly formed on any one spot, and might there maintain itself in a body and afterward spread, so that the individuals of the new variety would chiefly cross together. On this principle, nurserymen always prefer saving seed from a large body of plants, as the chance of intercrossing is thus lessened. Even with animals which unite for each birth, and which do not propagate rapidly, we must not assume that free intercrossing would always eliminate the effects of natural selection, for I can bring forward a considerable body of facts showing that within the same area two varieties of the same animal may long remain distinct, from haunting different stations, from breeding at slightly different seasons, or from the individuals of each variety preferring to pair together. Intercrossing plays a very important part in nature by keeping the individuals of the same species or of the same variety true and uniform in character. It will obviously thus act far more efficiently with those animals which unite for each birth, but, as already stated, we have reason to believe that occasional intercrosses take place with all animals and plants. Even if these take place only at long intervals of time, the young thus produced will gain so much in vigour and fertility over the offspring from long-continued self-fertilisation that they will have a much better chance of surviving and propagating their kind, and thus in the long run the influence of crosses, even at rare intervals, will be great. With respect to organic beings extremely low in the scale, which do not propagate sexually, nor conjugate, and which cannot possibly intercross, uniformity of character can be retained by them under the same conditions of life only through the principle of inheritance, and through natural selection, which will destroy any individuals departing from the proper type. If the conditions of life change, and the form undergoes modification, uniformity of character can be given to the modified offspring solely by natural selection preserving similar favourable variations. Isolation also is an important element in the modification of species through natural selection. In a confined or isolated area, if not very large, the organic and inorganic conditions of life will generally be almost uniform, so that natural selection will tend to modify all the varying individuals of the same species in the same manner. Intercrossing with the inhabitants of the surrounding districts will also be thus prevented. Moritz Wagner has lately published an interesting essay on this subject, and has shown that the service rendered by isolation in preventing crosses between newly formed varieties is probably greater even than I supposed. But from reasons already assigned, I can by no means agree with this naturalist that migration and isolation are necessary elements for the formation of new species. The importance of isolation is likewise great in preventing, after any physical change in the conditions, such as of climate, elevation of the land, etc., the immigration of better adapted organisms, and thus new places in the natural economy of the district will be left open to be filled up by the modification of the old inhabitants. Lastly, isolation will give time for a new variety to be improved at a slow rate, and this may sometimes be of much importance. If, however, an isolated area be very small, either from being surrounded by barriers, or from having very peculiar physical conditions, the total number of the inhabitants will be small, and this will retard the production of new species through natural selection by decreasing the chances of favourable variations arising. The mere lapse of time by itself does nothing either for or against natural selection. I state this because it has been erroneously asserted that the element of time has been assumed by me to play an all-important part in modifying species, as if all the forms of life were necessarily undergoing change through some innate law. Lapse of time is only so far important, and its importance in this respect is great, that it gives a better chance of beneficial variations arising and of their being selected, accumulated and fixed. It likewise tends to increase the direct action of the physical conditions of life in relation to the constitution of each organism. If we turn to nature to test the truth of these remarks, and look at any small isolated area, such as an oceanic island, although the number of the species inhabiting it is small, as we shall see in our chapter on geographic distribution, yet of these species a very large proportion are endemic, that is, have been produced there and nowhere else in the world. Hence an oceanic island at first sight seems to have been highly favourable for the production of new species. But we may thus deceive ourselves, for to ascertain whether a small isolated area or a large open area like a continent has been most favourable for the production of new organic forms, we ought to take the comparison within equal times, and this we are incapable of doing. Although isolation is of great importance in the production of new species, on the whole I am inclined to believe that largeness of area is still more important, especially for the production of species which shall prove capable of enduring for a long period and of spreading widely. Throughout a great and open area, not only will there be a better chance of favourable variations, arising from the large number of individuals of the same species there supported, but the conditions of life are much more complex from the large number of already existing species, and if some of these many species become modified and improved, others will have to be improved in a corresponding degree, or they will be exterminated. Each new form also, as soon as it has been much improved, will be able to spread over the open and continuous area, and will thus come into competition with many other forms. Moreover, great areas, though now continuous, will often, owing to former oscillations of level, have existed in a broken condition, so that the good effects of isolation will generally, to a certain extent, have concurred. Finally, I conclude that, although small isolated areas have been in some respects highly favourable for the production of new species, yet that the course of modification will generally have been more rapid in large areas, and what is more important, that the new forms produced on large areas, which already have been victorious over many competitors, will be those that will spread most widely, and will give rise to the greatest number of new varieties and species. They will thus play a more important part in the changing history of the organic world. In accordance with this view, we can perhaps understand some facts which will be again alluded to in our chapter on geographical distribution. For instance, the fact of the productions of the smaller continent of Australia now yielding before those of the larger Europeo-Asiatic area. Thus also it is that continental productions have everywhere become so largely naturalized on islands. On a small island the race for life will have been less severe, and there will have been less modification and less extermination. Hence we can understand how it is that the flora of Madeira, according to Oswald here, resembles to a certain extent the extinct tertiary flora of Europe. All freshwater basins taken together make a small area compared with that of the sea or of the land. Consequently, the competition between freshwater productions will have been less severe than elsewhere. New forms will have been more slowly produced, and old forms more slowly exterminated. And it is in freshwater basins that we find 7 genera of gonoid fishes, remnants of a once preponderant order. And in freshwater we find some of the most anomalous forms now known in the world, as the Ornithorhynchus and Lepidosiren, which, like fossils, connect to a certain extent orders at present widely separated in the natural scale. These anomalous forms may be called living fossils. They have endured to the present day from having inhabited a confined area, and from having been exposed to less varied and therefore less severe competition. To sum up, as far as the extreme intricacy of the subject permits, the circumstances favourable and unfavourable for the production of new species through natural selection, I conclude that for terrestrial productions, a large continental area which has undergone many oscillations of level will have been the most favourable for the production of many new forms of life, fitted to endure for a long time and to spread widely. While the area existed as a continent, the inhabitants will have been numerous in individuals and kinds, and will have been subjected to severe competition. When converted by subsistence into large separate islands, there will still have existed many individuals of the same species on each island. Intercrossing on the confines of the range of each new species will have been checked. After physical changes of any kind, immigration will have been prevented, so that new places in the polity of each island will have had to be filled up by the modification of the old inhabitants, and time will have been allowed for the varieties in each to become well modified and perfected. When, by renewed elevation, the islands were reconverted into a continental area, there will again have been very severe competition. The most favoured or improved varieties will have been enabled to spread. There will have been much extinction of the less improved forms, and the relative proportional numbers of the various inhabitants of the reunited continent will again have been changed, and again there will have been a fair field for natural selection to improve still further the inhabitants, and thus to produce new species. That natural selection generally acts with extreme slowness, I fully admit. It can only act when there are places in the natural polity of a district which can be better occupied by the modification of some of its existing inhabitants. The occurrence of such places will often depend on physical changes, which generally take place very slowly, and on the immigration of better adapted forms being prevented. As some few of the old inhabitants become modified, the mutual relations of others will often be disturbed, and this will create new places ready to be filled up by better adapted forms. but all this will take place very slowly. Although all the individuals of the same species differ in some slight degree from each other, it would often be long before differences of the right nature in various parts of the organisation might occur. The result would often be greatly retarded by free intercrossing. Many will exclaim that these several causes are amply sufficient to neutralize the power of natural selection. I do not believe so, but I do believe that natural selection will generally act very slowly, only at long intervals of time, and only on a few of the inhabitants of the same region. I further believe that these slow intermittent results accord well with what geology tells us of the rate and manner at which the inhabitants of the world have changed. Slow though the process of selection may be, if feeble man can do much by artificial selection, I can see no limit to the amount of change, to the beauty and complexity of the co-adaptations between all organic beings, one with another, and with their physical conditions of life, which may have been effected in the long course of time through nature's power of selection, that is, by the survival of the fittest. Extinction caused by natural selection. This subject will be more fully discussed in our chapter on geology, but it must here be alluded to, from being intimately connected with natural selection. Natural selection acts solely through the preservation of variations in some way advantageous, which consequently endure. Owing to the high geometrical rate of increase of all organic beings, each area is already fully stocked with inhabitants, and it follows from this that as the favoured forms increase in number, so generally will the less favoured decrease and become rare. Rarity, as geology tells us, is the precursor to extinction. We can see that any form which is represented by few individuals will run a good chance of utter extinction during great fluctuations in the nature or the seasons, or from a temporary increase in the number of its enemies. But we may go further than this, for as new forms are produced, unless we admit that specific forms can go on indefinitely increasing in number, many old forms must become extinct. That the number of specific forms has not indefinitely increased, geology plainly tells us, and we shall presently attempt to show why it is that the number of species throughout the world has not become immeasurably great. We have seen that the species which are most numerous in individuals have the best chance of producing favourable variations within any given period. We have evidence of this in the fact stated in the second chapter, showing that it is the common and diffused or dominant species which offer the greatest number of recorded varieties. Hence, rare species will be less quickly modified or improved within any given period. They will consequently be beaten in the race for life by the modified and improved descendants of the commoner species. From these several considerations, I think it inevitably follows that as new species in the course of time are formed through natural selection, others will become rarer and finally extinct. The forms which stand in closest competition with those undergoing modification and improvement will naturally suffer most, and we have seen in the chapter on the struggle for existence that it is the most closely allied forms, varieties of the same species, and species of the same genus or related genera, which, from having nearly the same structure, constitution, and habits, generally come into the severest competition with each other. Consequently, each new variety or species, during the progress of its formation, will generally press hardest on its nearest kindred and tend to exterminate them. We see the same process of extermination among our domesticated productions, through the selection of improved forms by man. Many curious instances could be given showing how quickly new breeds of cattle, sheep, and other animals, and varieties of flowers, take the place of older and inferior kinds. In Yorkshire it is historically known that the ancient black cattle were displaced by the longhorns, and that these were swept away by the shorthorns, I quote the words of an agricultural writer, as if by some murderous pestilence. Divergence of character. The principle which I have designated by this term is of high importance, and explains, as I believe, several important facts. In the first place, varieties, even strongly marked ones, though having somewhat of the character of species, as is shown by the hopeless doubts in many cases how to rank them, yet certainly differ far less from each other than do good and distinct species. Nevertheless, according to my view, varieties are species in the process of formation, and are, as I have called them, incipient species. How then does the lesser difference between varieties become augmented into the greater difference between species? That this does habitually happen, we must infer from most of the innumerable species throughout nature presenting well-marked differences, whereas varieties, the supposed prototypes and parents of future well-marked species, present slight and ill-defined differences. Mere chance, as we may call it, might cause one variety to differ in some character from its parents, and the offspring of this variety again to differ from its parent in the very same character and in a greater degree. But this alone would never account for so habitual and large a degree of difference as that between the species of the same genus. As has always been my practice, I have sought light on this head from our domestic productions. We shall here find something analogous. It will be admitted that the production of races so different as Shorthorn and Hereford cattle, race and cart horses, the several breeds of pigeons, etc., could never have been effected by the mere chance accumulation of similar variations during many successive generations. In practice, a fancier is, for instance, struck by a pigeon having a slightly shorter beak. Another fancier is struck by a pigeon having a rather longer beak, and on the acknowledged principle that fanciers do not and will not admire a medium standard, but like extremes, they both go on, as has actually occurred with the sub-breeds of the tumbler pigeon, choosing and breeding from birds with longer and longer beaks, or with shorter and shorter beaks. Again, we may suppose that at an early period of history, the men of one nation or district required swifter horses, while those of another required stronger and bulkier horses. The early differences would be very slight, but in the course of time, from the continued selection of swifter horses in the one case and of stronger ones in the other, the differences would become greater and would be noted as forming two sub-breeds. Ultimately, after the lapse of centuries, these sub-breeds would become converted into two well-established and distinct breeds. As the differences became greater, the inferior animals with intermediate characters, being neither very swift nor very strong, would not have been used for breeding, and will thus have tended to disappear. Here, then, we see in man's productions the action of what may be called the principle of divergence, causing differences, at first barely appreciable, steadily to increase, and the breeds to diverge in character, both from each other and from their common parent. But how, it may be asked, can any analogous principle apply in nature? I believe it can and does apply most efficiently, though it was a long time before I saw how, from the simple circumstance that the more diversified the descendants from any one species become, in structure, constitution and habits, by so much will they be better enabled to seize on many and widely diversified places in the polity of nature, and so be enabled to increase in numbers. We can clearly discern this in the case of animals with simple habits. Take the case of a carnivorous quadruped, of which the number that can be supported in any country has long ago arrived at its full average. If its natural power of increase be allowed to act, it can succeed in increasing, the country not undergoing any change in conditions, only by its varying descendants seizing on places at present occupied by other animals, some of them, for instance, being enabled to feed on new kinds of prey, either dead or alive, some inhabiting new stations, climbing trees, frequenting water, and some perhaps becoming less carnivorous. The more diversified in habits and structure the descendants of our carnivorous animals become, the more places they will be enabled to occupy. What applies to one animal will apply throughout all time to all animals, that is, if they vary, for otherwise natural selection can effect nothing. So it will be with plants. It has been experimentally proved that if a plot of ground be sown with one species of grass, and a similar plot be sown with several distinct genera of grasses, a greater number of plants and a greater weight of dry herbage can be raised in the latter than in the former case. The same has been found to hold good when one variety and several mixed varieties of wheat have been sown on equal spaces of ground. Hence, if any one species of grass were to go on varying, and the varieties were continually selected which differed from each other in the same manner, though in a very slight degree, as do the distinct species and genera of grasses, a greater number of individual plants of this species, including its modified descendants, would succeed in living on the same piece of ground. And we know that each species and each variety of grass is annually sowing almost countless seeds, and is thus striving, as it may be said, to the utmost to increase in number. Consequently, in the course of many thousand generations, the most distinct varieties of any one species of grass would have the best chance of succeeding and of increasing in numbers, and thus of supplanting the less distinct varieties, and varieties, when rendered very distinct from each other, take the rank of species. The truth of the principle that the greatest amount of life can be supported by great diversification of structure is seen under many natural circumstances. In an extremely small area, especially if freely open to immigration, and where the contest between individual and individual must be very severe, we always find great diversity in its inhabitants. For instance, I found that a piece of turf, 3 feet by 4 in size, which had been exposed for many years to exactly the same conditions, supported 20 species of plants, and these belonged to 18 genera, and to 8 orders, which shows how much these plants differed from each other. So it is with the plants and insects on small and uniform islets, also in small ponds of fresh water. Farmers find that they can raise more food by a rotation of plants belonging to the most different orders. Nature follows what may be called a simultaneous rotation. Most of the animals and plants which live close around any small piece of ground could live on it, supposing its nature not to be in any way peculiar, and may be said to be striving to the utmost to live there. But it is seen that where they come into closest competition, the advantages of diversification of structure, with the accompanying differences of habit and constitution, determine that the inhabitants, which thus jostle each other most closely, shall, as a general rule, belong to what we call different genera and orders. The same principle is seen in the naturalization of plants through man's agency in foreign lands. It might have been expected that the plants which would succeed in becoming naturalized in any land would generally have been closely allied to the indigenes, for these are commonly looked at as especially created and adapted for their own country. It might also perhaps have been expected that naturalized plants would have belonged to a few groups more especially adapted to certain stations in their own homes. But the case is very different. And Alphonse de Candolle has well remarked, in his great and admirable work, that floras gain by naturalization proportionally with the number of the native genera and species, far more in new genera than in new species. To give a single instance, in the last edition of Dr. Asa Gray's Manual of the Flora of the Northern United States, 260 naturalized plants are enumerated, and these belong to 162 genera. We thus see that these naturalized plants are of a highly diversified nature. They differ, moreover, to a large extent from the indigenes, for out of the 162 naturalized genera, no less than 100 genera are not there indigenous, and thus a large proportional addition is made to the genera now living in the United States. By considering the nature of the plants or animals which have in any country struggled successfully with the indigenes, and have there become naturalized, we may gain some crude idea in what manner some of the natives would have had to be modified in order to gain an advantage over their compatriots, and we may at least infer that diversification of structure amounting to new generic differences would be profitable to them. The advantage of diversification of structure in the inhabitants of the same region is, in fact, the same as that of the physiological division of labour in the organs of the same individual body, a subject so well elucidated by Milne Edwards. No physiologist doubts that a stomach, by being adapted to digest vegetable matter alone, or flesh alone, draws most nutriment from these substances. So in the general economy of any land, the more widely and perfectly the animals and plants are diversified for different habits of life, so will a greater number of individuals be capable of their supporting themselves. A set of animals, with their organisation but little diversified, could hardly compete with a set more perfectly diversified in structure. It may be doubted, for instance, whether the Australian marsupials, which are divided into groups differing but little from each other, and feebly representing, as Mr. Waterhouse and others have remarked, our carnivorous, ruminant and rodent mammals, could successfully compete with these well-developed orders. In the Australian animals we see the process of diversification in an early and incomplete stage of development. End of section 2 of chapter 4. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. The Origin of Species by Means of Natural Selection, or the Preservation of Favoured Races in the Struggle for Life. 6th London edition by Charles Darwin. Chapter number 4. Natural Selection, or the Survival of the Fittest. Section 3 of 3. The probable effects of the action of natural selection through divergence of character and extinction on the descendants of a common ancestor. After the foregoing discussion, which has been much compressed, we may assume that the modified descendants of any one species will succeed so much the better as they become more diversified in structure, and are thus enabled to encroach on places occupied by other beings. Now let us see how this principle of benefit being derived from divergence of character, combined with the principles of natural selection and of extinction, tends to act. The accompanying diagram will aid us in understanding this rather perplexing subject. Let A to L represent the species of a genus large in its own country. These species are supposed to resemble each other in unequal degrees, as is so generally the case in nature, and is represented in the diagram by the letters standing at unequal distances. I have said a large genus, because, as we saw in the second chapter, on an average more species vary in large genera than in small genera, and so the varying species of the large genera present a greater number of varieties. We have also seen that the species which are the commonest and most widely diffused vary more than do the rare and restricted species. Let A be a common, widely diffused and varying species, belonging to a genus large in its own country. The branching and diverging dotted lines of unequal lengths proceeding from A may represent its varying offspring. The variations are supposed to be extremely slight, but of the most diversified nature. They are not supposed all to appear simultaneously, but often after long intervals of time. Nor are they all supposed to endure for equal periods. Only those variations which are in some way profitable will be preserved or naturally selected. And here the importance of the principle of benefit derived from divergence of character comes in. for this will generally lead to the most different or divergent variations, represented by the outer dotted lines, being preserved and accumulated by natural selection. When a dotted line reaches one of the horizontal lines, and is there marked by a small numbered letter, a sufficient amount of variation is supposed to have been accumulated to form it into a fairly well-marked variety, such as would be thought worthy of record in a systematic work. The intervals between the horizontal lines in the diagram may represent each 1,000 or more generations. After 1,000 generations, species A is supposed to have produced two fairly well-marked varieties, namely A1 and M1. These two varieties will generally still be exposed to the same conditions which made their parents variable, and the tendency to variability is in itself hereditary. Consequently, they will likewise tend to vary, and commonly in nearly the same manner as did their parents. Moreover, these two varieties, being only slightly modified forms, will tend to inherit those advantages which made their parent, A, more numerous than most of the other inhabitants of the same country. They will also partake of those more general advantages which made the genus to which the parent species belonged a large genus in its own country. And all these circumstances are favourable to the production of new varieties. If, then, these two varieties be variable, the most divergent of their variations will generally be preserved during the next 1,000 generations, and after this interval, variety A1 is supposed in the diagram to have produced variety A2, which will, owing to the principle of divergence, differ more from A than did variety A1. Variety M1 is supposed to have produced two varieties, namely M2 and S2, differing from each other and more considerably from their common parent A. We may continue the process by similar steps for any length of time. Some of the varieties, after each 1,000 generations, producing only a single variety, but in a more and more modified condition, some producing 2 or 3 varieties, and some failing to produce any. Thus the varieties or modified descendants of the common parent A will generally go on increasing in number and diverging in character. In the diagram, the process is represented up to the 10,000th generation, and under a condensed and simplified form up to the 14,000th generation. But I must here remark that I do not suppose that the process ever goes on so regularly as is represented in the diagram, though in itself made somewhat irregular, nor that it goes on continuously. It is far more probable that each form remains for long periods unaltered, and then again undergoes modification. Nor do I suppose that the most divergent varieties are invariably preserved. A medium form may often long endure, and may or may not produce more than one modified descendant, for natural selection will always act according to the nature of the places which are either unoccupied or not perfectly occupied by other beings, and this will depend on infinitely complex relations. But as a general rule, the more diversified in structure the descendants from any one species can be rendered, the more places they will be enabled to seize on, and the more their modified progeny will increase. In our diagram, the line of succession is broken at regular intervals by small numbered letters marking the successive forms which have become sufficiently distinct to be recorded as varieties. But these breaks are imaginary, and might have been inserted anywhere, after intervals long enough to allow the accumulation of a considerable amount of divergent variation. As all the modified descendants from a common and widely diffused species belonging to a large genus will tend to partake of the same advantages which made their parent successful in life, they will generally go on multiplying in number, as well as diverging in character. This is represented in the diagram by the several divergent branches proceeding from A. The modified offspring from the later and more highly improved branches in the lines of descent will, it is probable, often take the place of, and so destroy, the earlier and less improved branches. This is represented in the diagram by some of the lower branches not reaching to the upper horizontal lines. In some cases, no doubt, the process of modification will be confined to a single line of descent, and the number of modified descendants will not be increased, although the amount of divergent modification may have been augmented. This case would be represented in the diagram if all the lines proceeding from A were removed, excepting that from A1 to A10. In the same way, the English racehorse and English pointer have apparently both gone on slowly diverging in character from their original stocks, without either having given off any fresh branches or races. After 10,000 generations, species A is supposed to have produced 3 forms, A10, F10 and M10, which, from having diverged in character during the successive generations, will have come to differ largely, but perhaps unequally, from each other and from their common parent. If we suppose the amount of change between each horizontal line in our diagram to be excessively small, these 3 forms may still be only well-marked varieties, but we have only to suppose the steps in the process of modification to be more numerous or greater in amount, to convert these 3 forms into doubtful, or at least into well-defined species. Thus, the diagram illustrates the steps by which the small differences distinguishing varieties are increased into the larger differences distinguishing species. By continuing the same process for a greater number of generations, as shown in the diagram in a condensed and simplified manner, we get 8 species, marked by the letters between A14 and M14, all descended from A. Thus, as I believe, species are multiplied and genera are formed. In a large genus, it is probable that more than one species will vary. In the diagram, I have assumed that a second species, I, has produced, by analogous steps, after 10,000 generations, either 2 well-marked varieties, W10 and Z10, or 2 species, according to the amount of change supposed to be represented between the horizontal lines. After 14,000 generations, 6 new species, marked by the letters N14 to Z14, are supposed to have been produced. In any genus, the species which are already very different in character from each other will generally tend to produce the greatest number of modified descendants, for these will have the best chance of seizing on new and widely different places in the polity of nature. Hence, in the diagram, I have chosen the extreme species A and the nearly extreme species I as those which have largely varied and have given rise to new varieties and species. the other 9 species, marked by capital letters, of our original genus may for long but unequal periods continue to transmit unaltered descendants, and this is shown in the diagram by the dotted lines unequally prolonged upwards. But during the process of modification represented in the diagram, another of our principles, namely that of extinction, will have played an important part. As in each fully stocked country, natural selection necessarily acts by the selected form having some advantage in the struggle for life over other forms, there will be a constant tendency in the improved descendants of any one species to supplant and exterminate in each stage of descent their predecessors and their original progenitor. For it should be remembered that the competition will generally be most severe between those forms which are most nearly related to each other in habits, constitution, and structure. Hence all the intermediate forms between the earlier and later states, that is between the less and more improved states of the same species, as well as the original parent species itself, will generally tend to become extinct. So it probably will be with many whole collateral lines of descent, which will be conquered by later and improved lines. If, however, the modified offspring of a species get into some distinct country, or become quickly adapted to some quite new station, in which offspring and progenitor do not come into competition, both may continue to exist. If then our diagram be assumed to represent a considerable amount of modification, species A and all the earlier varieties will have become extinct, being replaced by 8 new species, A14 to M14, and species I will be replaced by 6, N14 to Z14, new species. But we may go further than this. The original species of our genus were supposed to resemble each other in unequal degrees, as is so generally the case in nature. Species A being more nearly related to B, C, and D than to the other species, and species I more to G, H, K, and L than to the others. These 2 species, A and I, were also supposed to be very common and widely diffused species, so that they must originally have had some advantage over most of the other species of the genus. Their modified descendants, 14 in number at the 14,000th generation, will probably have inherited some of the same advantages. They have also been modified and improved in a diversified manner at each stage of descent, so as to have become adapted to many related places in the natural economy of their country. It seems, therefore, extremely probable that they will have taken the places of, and thus exterminated, not only their parents, A and I, but likewise some of the original species which were most nearly related to their parents. Hence, very few of the original species will have transmitted offspring to the 14,000th generation. We may suppose that only one, F, of the 2 species, E and F, which were least closely related to the other 9 original species, has transmitted descendants to this late stage of descent. The new species in our diagram, represented from the original 11 species, will now be 15 in number. Owing to the divergent tendency of natural selection, the extreme amount of difference in character between species A14 and Z14 will be much greater than that between the most distinct of the original 11 species. The new species, moreover, will be allied to each other in a widely different manner. Of the 8 descendants from A, the 3 marked A14, Q14 and P14 will be nearly related, having recently branched off from A10. B14 and F14, from having diverged at an earlier period from A5, will be in some degree distinct from the 3 first named species. And lastly, O14, E14 and M14 will be nearly related one to the other, but, from having diverged at the first commencement of the process of modification, will be widely different from the other 5 species, and may constitute a subgenus or a distinct genus. The 6 descendants from I will form 2 subgenera or genera, but as the original species I differed largely from A, standing nearly at the extreme end of the original genus, the 6 descendants from I will, owing to inheritance alone, differ considerably from the 8 descendants from A. The 2 groups, moreover, are supposed to have gone on diverging in different directions. The intermediate species also, and this is a very important consideration, which connected the original species A and I, have all become, except F, extinct and have left no descendants. Hence the 6 new species descended from I, and the 8 descendants from A, will have to be ranked as very distinct genera, or even as distinct subfamilies. Thus it is, as I believe, that 2 or more genera are produced by descent with modification from 2 or more species of the same genus, and the 2 or more parent species are supposed to be descended from some one species of an earlier genus. In our diagram, this is indicated by the broken lines beneath the capital letters, converging in sub-branches downwards towards a single point. This point represents a species, the supposed progenitor of our several new subgenera and genera. It is worth while to reflect for a moment on the character of the new species F14, which is supposed not to have diverged much in character, but to have retained the form of F, either unaltered or altered only in a slight degree. In this case, its affinities to the other 14 new species will be of a curious and circuitous nature. Being descended from a form that stood between the parent species A and I, now supposed to be extinct and unknown, it will be in some degree intermediate in character between the 2 groups descended from these 2 species. But as these 2 groups have gone on diverging in character from the type of their parents, the new species F14 will not be directly intermediate between them, but rather between types of the 2 groups, and every naturalist will be able to call such cases before his mind. In the diagram, each horizontal line has hitherto been supposed to represent 1,000 generations, but each may represent 1,000,000 or more generations. It may also represent a section of the successive strata of the earth's crust, including extinct remains. We shall, when we come to our chapter on geology, have to refer again to this subject, and I think we shall then see that the diagram throws light on the affinities of extinct beings, which, though generally belonging to the same orders, families or genera with those now living, yet are often, in some degree, intermediate in character between existing groups, and we can understand this fact, for the extinct species lived at various remote epochs when the branching lines of descent had diverged less. I see no reason to limit the process of modification, as now explained, to the formation of genera alone. If in the diagram we suppose the amount of change represented by each successive group of diverging dotted lines to be great, the forms marked A14 to P14, those marked B14 and F14, and those marked O14 to M14 will form 3 very distinct genera. We shall also have 2 very distinct genera descended from I, differing widely from the descendants of A. These 2 groups of genera will thus form 2 distinct families or orders, according to the amount of divergent modification supposed to be represented in the diagram. And the 2 new families or orders are descended from 2 species of the original genus, and these are supposed to be descended from some still more ancient and unknown form. We have seen that in each country it is the species belonging to the larger genera which oftenest present varieties or incipient species. This indeed might have been expected, for as natural selection acts through one form having some advantage over other forms in the struggle for existence, it will chiefly act on those which already have some advantage, and the largeness of any group shows that its species have inherited from a common ancestor some advantage in common. Hence the struggle for the production of new and modified descendants will mainly lie between the larger groups, which are all trying to increase in number. One large group will slowly conquer another large group, reduce its number, and thus lessen its chance of further variation and improvement. Within the same large group, the later and more highly perfected subgroups, from branching out and seizing on many new places in the polity of nature, will constantly tend to supplant and destroy the earlier and less improved subforms. Small and broken groups and subgroups will finally disappear. Looking to the future, we can predict that the groups of organic beings which are now large and triumphant, and which are least broken up, that is, which have as yet suffered least extinction, will for a long period continue to increase. But which groups will ultimately prevail, no man can predict, for we know that many groups, formerly most extensively developed, have now become extinct. Looking still more remotely to the future, we may predict that, owing to the continued and steady increase of the larger groups, a multitude of smaller groups will become utterly extinct and leave no modified descendants, and consequently that, of the species living at any one period, extremely few will transmit descendants to a remote futurity. I shall have to return to this subject in the chapter on classification, but I may add that as, according to this view, extremely few of the more ancient species have transmitted descendants to the present day, and as all the descendants of the same species form a class, we can understand how it is that there exist so few classes in each main division of the animal and vegetable kingdoms. Although few of the most ancient species have left modified descendants, yet at remote geological periods the earth may have been almost as well peopled with species of many genera, families, orders and classes as at the present day. On the degree to which organisation tends to advance, Natural selection acts exclusively by the preservation and accumulation of variations, which are beneficial under the organic and inorganic conditions to which each creature is exposed at all periods of life. The ultimate result is that each creature tends to become more and more improved in relation to its conditions. This improvement invariably leads to the gradual advancement of the organisation of the greater number of living beings throughout the world. But here we enter on a very intricate subject, for naturalists have not defined to each other's satisfaction what is meant by an advance in organisation. Among the vertebra, the degree of intellect and an approach in structure to man clearly come into play. It might be thought that the amount of change which the various parts and organs pass through in their development from embryo to maturity would suffice as a standard of comparison. But there are cases, as with certain parasitic crustaceans, in which several parts of the structure become less perfect, so that the mature animal cannot be called higher than its larva. Von Baer's standard seems the most widely applicable and the best, namely the amount of differentiation of the parts of the same organic being in the adult state, as I should be inclined to add, and their specialisation for different functions, or, as Milne-Edwards would express it, the completeness of the division of physiological labour. But we shall see how obscure this subject is if we look, for instance, to fishes, among which some naturalists rank those as highest which, like the sharks, approach nearest to amphibians, while other naturalists rank the common bony or teleostean fishes as the highest, inasmuch as they are most strictly fish-like, and differ most from the other vertebrate classes. We see still more plainly the obscurity of the subject by turning to plants, among which the standard of intellect is of course quite excluded. And here some botanists rank those plants as highest which have every organ, as sepals, petals, stamens and pistils, fully developed in each flower, whereas other botanists, probably with more truth, look at the plants which have their several organs much modified and reduced in number as the highest. If we take as the standard of high organisation the amount of differentiation and specialisation of the several organs in each being when adult, and this will include the advancement of the brain for intellectual purposes, natural selection clearly leads towards this standard, for all physiologists admit that the specialisation of organs, inasmuch as in this state they perform their functions better, is an advantage to each being, and hence the accumulation of variations tending towards specialisation is within the scope of natural selection. On the other hand, we can see, bearing in mind that all organic beings are striving to increase at a high ratio, and to seize on every unoccupied or less well occupied space in the economy of nature, that it is quite possible for natural selection gradually to fit a being to a situation in which several organs would be superfluous or useless. In such cases there would be retrogression in the scale of organisation. Whether organisation on the whole has actually advanced from the remotest geological periods to the present day will be more conveniently discussed in our chapter on geological succession. But it may be objected that if all organic beings thus tend to rise in the scale, how is it that throughout the world a multitude of the lowest forms still exist? And how is it that in each great class some forms are far more highly developed than others? why have not the more highly developed forms everywhere supplanted and exterminated the lower? Lamarck, who believed in an innate and inevitable tendency towards perfection in all organic beings, seems to have felt this difficulty so strongly that he was led to suppose that new and simple forms are continually being produced by spontaneous generation. Science has not as yet proved the truth of this belief, whatever the future may reveal. On our theory, the continued existence of lowly organisms offers no difficulty, for natural selection, or the survival of the fittest, does not necessarily include progressive development. It only takes advantage of such variations as arise and are beneficial to each creature under its complex relations of life. And it may be asked what advantage, as far as we can see, would it be to an infusorian animalcule, to an intestinal worm, or even to an earthworm, to be highly organised? If it were no advantage, these forms would be left by natural selection unimproved or but little improved, and might remain for indefinite ages in their present lowly condition. And geology tells us that some of the lowest forms, as the infusoria and rhizopods, have remained for an enormous period in nearly their present state. But to suppose that most of the many now existing low forms have not in the least advanced since the first dawn of life would be extremely rash, for every naturalist who has dissected some of the beings now ranked as very low in the scale must have been struck with their really wondrous and beautiful organisation. Nearly the same remarks are applicable if we look to the different grades of organisation within the same great group, for instance, in the vertebrata, to the coexistence of mammals and fish; among Mammalia, to the coexistence of man and the Ornithorhynchus; among fishes, to the coexistence of the shark and the lancelet, Amphioxus, which latter fish, in the extreme simplicity of its structure, approaches the invertebrate classes. But mammals and fish hardly come into competition with each other. The advancement of the whole class of mammals, or of certain members of this class, to the highest grade would not lead to their taking the place of fishes. Physiologists believe that the brain must be bathed by warm blood to be highly active, and this requires aerial respiration, so that warm-blooded animals, when inhabiting the water, lie under a disadvantage in having to come continually to the surface to breathe. With fishes, members of the shark family would not tend to supplant the lancelet, for the lancelet, as I hear from Fritz Müller, has as sole companion and competitor on the barren sandy shore of South Brazil an anomalous annelid. The three lowest orders of mammals, namely marsupials, edentata, and rodents, coexist in South America in the same region with numerous monkeys, and probably interfere little with each other. Although organisation on the whole may have advanced and be still advancing throughout the world, yet the scale will always represent many degrees of perfection, for the high advancement of certain whole classes, or of certain members of each class, does not at all necessarily lead to the extinction of those groups with which they do not enter into close competition. In some cases, as we shall hereafter see, lowly organised forms appear to have been preserved to the present day, from inhabiting confined or peculiar stations, where they have been subjected to less severe competition, and where their scanty numbers have retarded the chance of favourable variations arising. Finally, I believe that many lowly organised forms now exist throughout the world from various causes. In some cases, variations or individual differences of a favourable nature may never have arisen for natural selection to act on and accumulate. In no case, probably, has time sufficed for the utmost possible amount of development. In some few cases there has been what we must call retrogression of organisation, but the main cause lies in the fact that under very simple conditions of life, a high organisation would be of no service, possibly would be of actual disservice, as being of a more delicate nature and more liable to be put out of order and injured. Looking to the first dawn of life, when all organic beings, as we may believe, presented the simplest structure, how, it has been asked, could the first step in the advancement or differentiation of parts have arisen? Mr. Herbert Spencer would probably answer that, as soon as simple unicellular organisms came by growth or division to be compounded of several cells, or became attached to any supporting surface, his law that homologous units of any order become differentiated in proportion as their relations to incident forces become different, would come into action. But as we have no facts to guide us, speculation on the subject is almost useless. It is, however, an error to suppose that there would be no struggle for existence, and consequently no natural selection, until many forms had been produced. Variations in a single species inhabiting an isolated station might be beneficial, and thus the whole mass of individuals might be modified, or two distinct forms might arise. But, as I remarked towards the close of the introduction, no one ought to feel surprise at much remaining as yet unexplained on the origin of species, if we make due allowance for our profound ignorance on the mutual relations of the inhabitants of the world at the present time, and still more so during past ages. Convergence of character. Mr. H. C. Watson thinks that I have overrated the importance of divergence of character, in which, however, he apparently believes, and that convergence, as it may be called, has likewise played a part. If two species belonging to two distinct, though allied genera, had both produced a large number of new and divergent forms, it is conceivable that these might approach each other so closely that they would have all to be classed under the same genus, and thus the descendants of two distinct genera would converge into one. But it would in most cases be extremely rash to attribute to convergence a close and general similarity of structure in the modified descendants of widely distinct forms. The shape of a crystal is determined solely by the molecular forces, and it is not surprising that dissimilar substances should sometimes assume the same form. But with organic beings we should bear in mind that the form of each depends on an infinitude of complex relations, namely on the variations which have arisen, these being due to causes far too intricate to be followed out, on the nature of the variations which have been preserved or selected, and this depends on the surrounding physical conditions, and in a still higher degree on the surrounding organisms with which each being has come into competition, and lastly on inheritance, in itself a fluctuating element, from innumerable progenitors, all of which have had their forms determined through equally complex relations. It is incredible that the descendants of two organisms which had originally differed in a marked manner should ever afterwards converge so closely as to lead to a near approach to identity throughout their whole organisation. If this had occurred, we should meet with the same form, independently of genetic connection, recurring in widely separated geological formations, and the balance of evidence is opposed to any such admission. Mr. Watson has also objected that the continued action of natural selection, together with divergence of character, would tend to make an indefinite number of specific forms. As far as mere inorganic conditions are concerned, it seems probable that a sufficient number of species would soon become adapted to all considerable diversities of heat, moisture, etc. But I fully admit that the mutual relations of organic beings are more important, and as the number of species in any country goes on increasing, the organic conditions of life must become more and more complex. Consequently, there seems at first no limit to the amount of profitable diversification of structure, and therefore no limit to the number of species which might be produced. We do not know that even the most prolific area is fully stocked with specific forms. At the Cape of Good Hope and in Australia, which support such an astonishing number of species, many European plants have become naturalized. But geology shows us that from an early part of the Tertiary period, the number of species of shells, and that from the middle part of this same period, the number of mammals, has not greatly or at all increased. What then checks an indefinite increase in the number of species? The amount of life, and I do not mean the number of specific forms, supported on an area must have a limit, depending so largely as it does on physical conditions. Therefore, if an area be inhabited by very many species, each or nearly each species will be represented by few individuals, and such species will be liable to extermination from accidental fluctuations in the nature of the seasons, or in the number of their enemies. The process of extermination in such cases would be rapid, whereas the production of new species must always be slow. Imagine the extreme case of as many species as individuals in England, and the first severe winter or very dry summer would exterminate thousands on thousands of species. Rare species, and each species will become rare if the number of species in any country becomes indefinitely increased, will, on the principle often explained, present within a given period few favourable variations. Consequently, the process of giving birth to new specific forms would thus be retarded. When any species becomes very rare, close interbreeding will help to exterminate it. Authors have thought that this comes into play in accounting for the deterioration of the aurochs in Lithuania, of red deer in Scotland, and of bears in Norway, etc. Lastly, and this I am inclined to think is the most important element, a dominant species, which has already beaten many competitors in its own home, will tend to spread and supplant many others. Alphonse de Candolle has shown that those species which spread widely tend generally to spread very widely. Consequently, they will tend to supplant and exterminate several species in several areas, and thus check the inordinate increase of specific forms throughout the world. Dr. Hooker has recently shown that in the southeast corner of Australia, where, apparently, there are many invaders from different quarters of the globe, the endemic Australian species have been greatly reduced in number. How much weight to attribute to these several considerations I will not pretend to say, but conjointly they must limit in each country the tendency to an indefinite augmentation of specific forms. Summary of chapter. If under changing conditions of life, organic beings present individual differences in almost every part of their structure, and this cannot be disputed, if there be, owing to their geometrical rate of increase, a severe struggle for life at some age, season or year, and this certainly cannot be disputed, then, considering the infinite complexity of the relations of all organic beings to each other and to their conditions of life, causing an infinite diversity in structure, constitution and habits, to be advantageous to them, it would be a most extraordinary fact if no variations had ever occurred useful to each being's own welfare, in the same manner as so many variations have occurred useful to man. But if variations useful to any organic being ever do occur, assuredly individuals thus characterized will have the best chance of being preserved in the struggle for life. And from the strong principle of inheritance, these will tend to produce offspring similarly characterized. This principle of preservation, or the survival of the fittest, I have called natural selection. It leads to the improvement of each creature in relation to its organic and inorganic conditions of life, and consequently, in most cases, to what must be regarded as an advance in organization. Nevertheless, low and simple forms will long endure if well fitted for their simple conditions of life. Natural selection, on the principle of qualities being inherited at corresponding ages, can modify the egg, seed or young as easily as the adult. Among many animals, sexual selection will have given its aid to ordinary selection by assuring to the most vigorous and best adapted males the greatest number of offspring. Sexual selection will also give characters useful to the males alone in their struggles or rivalry with other males, and these characteristics will be transmitted to one sex or to both sexes, according to the form of inheritance which prevails. Whether natural selection has really thus acted in adapting the various forms of life to their several conditions and stations must be judged by the general tenor and balance of evidence given in the following chapters. But we have already seen how it entails extinction, and how largely extinction has acted in the world's history, geology plainly declares. Natural selection also leads to divergence of character, for the more organic beings diverge in structure, habits and constitution, by so much the more can a large number be supported on the area, of which we see proof by looking to the inhabitants of any small spot, and to the productions naturalized in foreign lands. Therefore, during the modification of the descendants of any one species, and during the incessant struggle of all species to increase in numbers, the more diversified the descendants become, the better will be their chance of success in the battle for life. Thus the small differences distinguishing varieties of the same species steadily tend to increase, till they equal the greater differences between species of the same genus, or even of distinct genera. We have seen that it is the common, the widely diffused and widely ranging species, belonging to the larger genera within each class, which vary most, and these tend to transmit to their modified offspring that superiority which now makes them dominant in their own countries. Natural selection, as has just been remarked, leads to divergence of character and to much extinction of the less improved and intermediate forms of life. On these principles, the nature of the affinities and the generally well-defined distinctions between the innumerable organic beings in each class throughout the world may be explained. It is a truly wonderful fact, the wonder of which we are apt to overlook from familiarity, that all animals and plants throughout all time and space should be related to each other in groups, subordinate to groups, in the manner which we everywhere behold, namely, varieties of the same species most closely related, species of the same genus less closely and unequally related, forming sections and subgenera, species of distinct genera much less closely related, and genera related in different degrees, forming subfamilies, families, orders, subclasses and classes. The several subordinate groups in any class cannot be ranked in a single file, but seem clustered around points, and these round other points, and so on in almost endless cycles. If species had been independently created, no explanation would have been possible of this kind of classification, but it is explained through inheritance and the complex action of natural selection, entailing extinction and divergence of character, as we have seen illustrated in the diagram. The affinities of all the beings of the same class have sometimes been represented by a great tree. I believe this simile largely speaks the truth. The green and budding twigs may represent existing species, and these produced during former years may represent the long succession of extinct species. At each period of growth, all the growing twigs have tried to branch out on all sides, and to overtop and kill the surrounding twigs and branches. In the same manner as species and groups of species have at all times overmastered other species in the great battle for life. The limbs divided into great branches, and these into lesser and lesser branches, were themselves once, when the tree was young, budding twigs, and this connection of the former and present buds by ramifying branches may well represent the classification of all extinct and living species in groups subordinate to groups. Of the many twigs which flourished when the tree was a mere bush, only 2 or 3, now grown into great branches, yet survive and bear the other branches. So with the species which lived during long past geological periods, very few have left living and modified descendants. From the first growth of the tree, many a limb and branch has decayed and dropped off, and these fallen branches of various sizes may represent those whole orders, families and genera which have now no living representatives, and which are known to us only in a fossil state. As we here and there see a thin, straggling branch springing from a fork low down in a tree, and which by some chance has been favoured and is still alive on its summit, so we occasionally see an animal like the Ornithorhynchus or Lepidosiren, which in some small degree connects by its affinities 2 large branches of life, and which has apparently been saved from fatal competition by having inhabited a protected station. As buds give rise by growth to fresh buds, and these, if vigorous, branch out and overtop on all sides many a feebler branch, so by generation I believe it has been with the great tree of life, which fills with its dead and broken branches the crust of the earth, and covers the surface with its ever-branching and beautiful ramifications. End of chapter 4.